Right. In fact, this is a day school. Day school means it's a discussion class. I briefly inform you about something about the course. This is level 4 inorganic chemistry course. So this is very important for you to continue further inorganic chemistry courses, particularly a level 5 course on organometallic chemistry. And you probably know nature does different reactions. For example, we'll take enzymes. All of these enzymes contain a metal center, or they are dressed with other ligands. So what we are looking at today, the basic coordination chemistry here, and where we look at some of the metals and very simple ligands such as ammonia and bidentate ligand as bipyridine or ethene, ene ligands. So I'll proceed soon after I mentioning. So there should be a plan for you to study. Now let's forget about what happened in level 3. Still you have a chance of getting a first class. So you should prepare for it, and without wasting your time, probably you should study, and probably you must visit the learn all yourself. There are a lot of information given in, particularly the questions. We have given MCQs for you to try out. What you call course wise, or the we have 4 books in this particular course: coordination chemistry, nuclear, and so on. So there are questions based on each book. So better try out. And there are 2 more practice tests for each CAT. And I must mention about the format of the CAT. Now this is an on-site exam. So therefore you have to come to the center, and the question paper will be containing 15 MCQs. Not only MCQs, but we have this time, we have some structured questions. So you got to work hard this time. We have to write something on the paper. So we will collect the answer script, and we will mark and we'll post it to you. So therefore, you got to work hard from the beginning. And so that's about the CAT exam. And if I start the the coordination chemistry one, I'll go further down. Right. So introduction to coordination chemistry. So I mentioned about there are ligands and there are metal ions or atoms. So central atom, each coordination compound has a metal center bonded to other molecules or ions. To take ligands, we normally look at whatever we looked at during A level, ammonia, chloride, and so on. Here we will be looking at a bit of more different types one. So ligand means each ligand has at least one pair of unshared electrons, which can be donated to a metal center to form a coordinate bond. And you know what is a coordinate bond means. A metal center got vacant orbital, and particularly the ligand got a pair of electrons that is donated to the metal center. So look at the basic anionic ligands, what we have here. Show the structure of the following ions. These actually whole thing is from your book. And remember, this presentation is given in your e-learn yourself. So you can download it and you can study well. And not only that, we have the recordings of last year. Dr. Kokila did different, probably 3 or 4 lectures or the day schools. The recordings are available, so you can visit them as well. This particular PowerPoint presentation also there, so you can go through it carefully. And it's basically contain what is in the book, right? So if you look at the carbonate, you know about carbonate, nitrate, oxalate, sulfate, and so on. So if you go over here, carbonate is a dianionic. There are 2 negative charges. There are 3 carbon, 3 oxygen atoms. So they are the nitrates, and this is the oxalate ion, and the sulfate. There are 2 negative charges. A metal can join from here. We call it a chelate in that sense, and we have thiosulfate. And if you look at the ligands here, we can classify them as neutral ligands or anionic type ligand. For example, the coordinating atom what is linked to the metal center, carbon here. Could be a carbon monoxide and ethylene molecule. Now, what we study these things during level 5 under organometallic. This is an organic ligand. So we look at that one next year, and the acetylenes and even benzene, we think it's a solvent, but it can coordinate. So cyanide is a negative one, the anionic one, right, which we have seen from A levels. If the coordination atom is nitrogen, there are various things we can have, the neutral ones. Nitrogen, we assume that 78% of the atmosphere contains nitrogen, but it's not that inert, it can coordinate to a metal center. And ammonia, we can convert N2 or the nitrogen into ammonia by simple processes. And that trialkyl amines, these are hydrazines, and so on. You can see the coordinating atom is nitrogen. Here it is going to be one nitrogen. Here we have two nitrogens. This is a ethylene diamine. We call it EN. There are two nitrogen donors, so we can coordinate two centers to a metal center, right? They are the negative ones. So we can go on like that with phosphorus. We have PH3, Br3, PX3, and these are what we call bidentate ligand. There are two phosphorus atoms. They are all neutral ones. But you can remove one of the phenols or get the negative ones as well. So there can be can join a metal center, PR, a PM, right? Even arsenic and oxygen or sulfur, they can have neutral ones, right? And the anionic one. So we have seen a carbon, oxygen ones, carbonate, sulfate, hydroxide, right? All that available here. Some are monoanionic, some are dianionic, right? So if you look at the DMSO can have oxygen coordination or sulfur coordination, right? So even the halogens can be neutral one, what we call fluorobenzene, can coordinate to a metal center, or fluoride as anionic one. So similarly, even the alkyl halide can coordinate and iodide here. So basically, we can get anything to coordinate to a metal center, provided the conditions are right. And sometimes they are not stable, so they can easily dissociate or decompose. So any question on these things? If you are not clear, you can ask question now. We are looking at the neutral ones, and we are looking at the anionic ones. Cationic ones are not going to coordinate. Okay, we'll move on. So I mentioned, if there is only one coordinating atom, we call it monodentate. Contain only one coordinating atom. Polydentate can have more than one, right? Contain more than one coordinating atom. So we can call it bidentate, tridentate, and so on. You can look at the book. You can easily see those ligands are classified. I'm not going to go into the book, but nice to look at them. Due to binding of more than one coordinating atom, a ring structure is formed. We call it chelation. These ligands are called chelating ligands. I mentioned earlier, EN, that is the EN ligand we have shown here. There are two CH2s, NH2, NH2, right? Ethylene diamine, it can coordinate to a metal center, platinum here in this case, and we have ClCl. And if you look at the platinum dichloride, this is called bipyridine. Only one side we call pyridine, and there's a bond between these two aryl ones, and we have bipyridine. Very similarly, again. So we have a chelate ring, and the ring size is 5. And these sort of small molecule with only two CH2s here cannot coordinate as a trans one. We call it trans here. Now they are cis to each other. Always it forms 6 geometry. So sometimes a single atom or ion can bridge two metals. That's what we are showing here. These are bridging ligands. For example, hydride, fluorides, chloride, and so on. Let's take the example. There are two metal centers. They are called binuclear. There are two atoms, metal atoms, binuclear. And there are simple ammonia, what we have seen it during A levels, donating a pair of electrons to make a bond. And then we have a Cl minus coordinating in the form of negative charge. And there's a lone pair on chlorine, it is donated here. So this Cl donating 2 electrons here. Sometimes we can call it, there are charged electrons between Cl and platinum. So these are called bridging ligands. You can have hydride here, you can have NH2 here, even O2 2 minus. We noticed earlier sulfate can make 2 bonds, and even the carbon monoxide can have it. So here, there's an example for carbon monoxide. There are cobalt centers and carbon monoxide. Normally we call it, there are triple bond. Now you have a double bond and it's shared with that other bond. So if you look at the composition here, there are 2 cobalt, right? And there are 8 carbon monoxides, 3 here, and 2. Now remember, when you are drawing and we are writing, cobalt means simple low. So exam point of view, sometimes people don't know what is carbon monoxide, what is cobalt. So here, capital low here, and here simple low here, right? The composition, 2 cobalt atom, and there are 8 carbon monoxide. We can write the same thing according to this molecular structure as well. So you can say 3 carbon monoxide, cobalt, we call it mu. There are 2 bridging ones, so 2 mu carbon monoxide, again cobalt, and carbon monoxide here. Now these are called terminal carbon monoxide, terminal bonds, and they are bridging bonds. In this case also, we have put 2 palladium, and there are 2 ammoniums, ammonia amine line, and there are 4. But remember, there are 2 of them are bridging, and 2 of them are terminal ones. If you have any questions in this one, you can ask now. Anything not clear? Actually, the day school means to discuss. So people have questions, so we can answer. So this information is given in page 5 of your book, right? If you go to page 5, you can see these structures are there. We call classification of ligands, right? And then page 6, you can see bidentate ligands, thirdentate ligands, tetradentate, hexadentate, and so on. Okay. So I move on to next slide now, or the next. So I'm not going to go through all thirdentate, tetradentate now. You should be able to read the book and should understand it, right? If I go here, now here calcium. And this particular ligand, we call it EDTA. You can see now, calcium is 2+, and EDTA going to be 4-. So therefore, balancing out, we have 2- at the end. So nitrogen here, and nitrogen is connected with 2 CH2s, and there are acetic acid bonds here, acetate. There are 4 oxygens bonded to calcium, and this has an octahedral geometry. These 4 in one plane, and 1 is coming out, and 1 is going inside. So this is an octahedral compound. Calcium, the coordination number is going to be 6. So if you look at that, the number of monodentate ligands or electron pairs coordinated or donated to a central atom is called the coordination number. So you know the oxidation number. Here, oxidation number of calcium is going to be 2+. Calcium normally prefers to remove 2 of the electrons and reach the noble gas electron configuration. So calcium 2+. And this ligand is 4 negatively charges. So ultimately you have 2 negative charges outside the bracket, right? So coordination number is going to be 6. There are 4 oxygen atoms and there are 2 nitrogen atoms. So I have given question number 2. What are the coordination number of the metal centers given? So I mentioned earlier, platinum, the coordination number from 2 here, the answer is given here now. Coordination of platinum is 4, 2 nitrogens. Ene means there are 2 nitrogen donors, and 2 Cl minus. So you have 4 here. Calcium case, you can see the structure here. There are 6, coordination number is 6, 2 nitrogens and 4 oxygens. The palladium in this particular compound, I have shown you earlier this particular compound. Here we have the composition, the number of palladium, number of ammonia molecules, and number of chloride ions. Now here you can see there are 2 bridging ones and 1 terminal one. We can write better way of putting this is this. The palladium center, the 1 terminal, and 1 terminal amine ligand, and there are 2 bridging ones and bridging these 2 metals. So this is a better way of expressing the earlier composition. So yeah, you should be able to draw the structure. If you have this information, you should be able to draw the structure, right? Anyway, coordination number, 1 palladium contains 1 Cl from this terminal, 1 ammonia ligand, and there are 2 bridging ones. Coordination number going to be 4. Right? In other words, there are 3 chlorine ligands and 1 ammonia. Similarly, molybdenum carbonyl, especially you will have to stop talking, right? Somebody is talking now, right? Okay. So coordination number here 6 carbons. Right? So anything to ask about now? Coordination number and oxidation number. Is it clear now? I mentioned about how to write a bridging compound, looking at the information given the structure. So if you know the structure, you can draw this information here easily. But if you know this information, you should be able to draw the structure as well. So let's move on to the next slide. So coordination number of a central atom in a coordination compound is depending on. So there are compounds being formed which depends on the oxidation of the metal. Sometimes we say palladium naught or 0 valent. Sometimes we have palladium 4+. If you look at the palladium naught, we have, even we can put more carbon monoxide or phosphine ligands. But if we have a palladium 4+, it prefers to get chloride or more negative ions. So therefore, the coordination number depends on ligands and the oxidation number of the metal. Nature of the ligand. Some are actually electron donors, some are electron withdrawing. We call them sigma donors, and we can call them pi acceptor. And the other thing actually, the size of the metal and the ligand. If the metal center is large one, or depending on 3D, 4D, 5D, and there will be different coordination numbers. And similarly, if the ligand is so bulky, containing a lot of phenyl ligands, phenyl substituents on a phosphine, so there will be different coordination numbers. And if you look at the coordination number here, and the geometry, and the number of d electrons present here, and some of the examples given. If you have coordination number, that means metal is bonded to 2 ligands. So we get them linear. And here I'm shown here, coordination number is 2, linear. They are far away from 180 degrees here, the 2 wells, right? An example is silver ammonium complex. We know silver chloride is a precipitate. So it's more like a covalent bonding. But if you add ammonia, it becomes a salt. So it could be dissolved in methanol or water, right? The quality increases as a salt, the solubility increases. You can see when you add ammonia, the silver chloride precipitate dissolves. The reason is that. So we can go through like that. And here gold compound. If you have the coordination number 3, trigonal planar. It's a planar structure here. They are far away as much as possible. The angle going to be 120. I think this you have learned during A levels. So I'm not going to go into more details here. So they are 120 degrees. They are in one plane, all that. Trigonal and planar. There are three, right? So the examples are given: silver with phosphine ligand 3, copper, right? And when you have the coordination number 4, there are two possibilities, but called tetrahedral and square plane. If you look at carbon compounds, they have tetrahedral arrangement. So when you are drawing something, now remember, very important, show the bonding pattern. Here you draw two things, A and A in one plane of the board. And one piece getting out of it, another one is getting inside. So they are tetrahedral geometry. But if you look at the square plane, whole thing in one plane. And the angle is about here 90. And here angle is about 109. So they are far away from each other. So remember, if you want to draw the structure, better here, square plane, there is one is always trans to another one. A to A is trans. So we call trans AA. And this case, A and A are cis to each other. They are very closer. And always A is trans to B now. Here B is trans to B. Here A is trans to A. Now here they are very called cis compound. In a tetrahedral compound, you can't call that. There's nothing is trans to that. A is not trans to anything. That's a vacant site, right? So remember, square plane and tetrahedral compounds, we will see later, particularly D10 compound form tetrahedral, D8 complexes with platinum, palladium, nickel, and so on, they form these square planar complexes, right? So there are two possibilities, D10 and D8, it's clearly mentioned here, right? And examples are given. In the case of coordination number 5, again, there are two possibilities. We call trigonal bipyramid. Trigonal bipyramid. This is trigonal. They are far away, like here, trigonal, 120 angle. There are two axial bonds now, axial links. And we call them, in the plane one, we call them equatorial. So this is one way of having 5 coordination number. That's the other way of having it, square pyramidal. Here, trigonal bipyramidal. Here, square pyramidal. So these 4 in one plane, and there's axial bond. And this side is vacant, right? So these are the two possibilities here. Example, iron pentacarbonate. So it is coordinatively saturated molecule with 18 electrons. And we'll look at the coordination number 6. D6. Normally, D6 compounds are octahedral. For example, here molybdenum hexacarbonate, right? So we have here. Now, remember, when you are drawing structures, be careful. Just don't connect them randomly. You need to have trans arrangement. The axial bonds here, these two getting out of the plane, and these are going into the plane. You can see what this L is trans to that one. If you draw that one and if you put another one here, and it's not right. So you won't be getting marks if the geometry is not right. Remember, all is given in the cover page. If you look at the cover page, we have shown it. Top one, trigonal, planar, and so on. Tetrahedron is there. So I have to emphasize that. Make sure you draw the right structure when you are answering. If the compound is octahedral, you have to draw this way. Draw this way and include ligands. Might be carbon monoxide, might be ammonia ligand here, might be a chloride ligand here. So all these combinations you can see. First put the metal center and make 6 bonds here, and they are trans to each other. Then you should be able to continue introducing ligands. So any questions from here? Now we are in page 9. Any questions? Anything not clear? Okay, let's move on. So group number, one of the important concepts actually getting the group number. Group number is equal to the sum of S and D electrons of the 0 valent Now this is zero valent, M0. The naked or the you can naturally found one with unreacted form. We have zero valent, not oxidized. Now here we have removed one electron, you get M plus. Some are removed 2 electrons. So D3, D2, D1. So similarly, you can write the whole spectrum here. But if you take this zero valent one, here D3 combining S and D. And so we have the group number 3. The scandium 4s1, 4s D2 like. So you can add on that one, you get all the added number here. In case we can take group 12, nickel group 10, cobalt, rhodium and iridium group 9. So that is the sum of S and D of the valence shell. So you should be able to remember at least these 3D elements: scandium, titanium, vanadium, chromium, manganese, and so on. So titanium is group 4 metal, right? So you can remove 4 electrons. Then when you remove 4 electrons, it becomes D0. There won't be any D electrons. So titanium 4 plus, similarly vanadium 5 plus, and so on. So at least you should be able to remember scandium to the zinc level. At least the other way actually you can remember from the Z value. 21 is scandium, chromium 24, and so on. So if you give the ZD is 24, you should be able to find out the group number that way. But remember at least some of the group numbers in the middle one. This is group 6, this is group 9, and this is group 12, right? So the other one, if you write the order, you should be able to find out the group number. That's quite important. So if you remove 0 valent 2 electrons, the D electron configuration is going to be 3. It's called Dn means D3, right? Okay, let's move on. Session 2. So if you have any queries, now what we are doing actually, we are going to a discussion class. We can't have a lecture within 2 hours to cover a whole book, right? So therefore, if you look at, we have up to page 15, we have given some information, and it says higher coordination numbers, D elements, electron configuration of 3D elements, and so on. And that information is given there in page 13. Scandium 21, and it's called argon configuration 4s2 3d1, and the group number is 3. So you should be able to calculate now, right? For example, zinc, we got Z is 30, and the electron configuration is argon 4s2 3d10. So adding 2 and 10 become 12. So group 12. Okay. So you should have some idea. At least I would say you should go through this book at least 3 times. First time, just browse it, see what is available in the book. Second time, go through carefully, making your highlighting, putting your own words sometimes, and putting your questions. This area is not clear to me, so you have to ask somebody, and you can write down your questions. Third time, you got to do all the exercises. You can look at the activities. You must do the what you call study questions and so on, and complete it third time. So if you have to do at least 3 times for you to get some good knowledge in that one, probably should be able to get an A at the end. And the summary is given, so in the point form, and the learning outcomes is given. Some activities are given in page 15. So before we move on to session 2, are there any questions from you? Have you got any questions from the audience here? What we have? Have you gone through the book? How about you? You understood whatever? How many? You went through the whole book? Maybe for the exam, we'll have to learn whole book, right? will be questions from, there are 8 sessions. We will be covering all that. And I must mention about people who came late. The cut paper will be different this time, not online, on-site exam paper. So there will be about 15 MCQs plus 2 structured ones. So you've got to study this time and you have to write something on the paper, not just ticking something, right? So you will be getting less mark if you don't write what is the question, right? Yeah, I think Dr. Kokla says she has put a model paper as well. So you should be knowing it. Did you notice that? Model paper.
Excuse me, sir. Excuse me, sir.
Yeah, answer the question. Ask the question.
Sir, so can you repeat the structure of the CAT exam?
We are going to have on-site exam paper. So there will be 15 MCQs, right? From book 1 and book 3. Book 1 and book 3, like last time. And there will be 2 structured questions. So the marks will be allocated 40-60. So 60 marks for the MCQs and 40 marks for the structured one.
There is a model paper uploaded.
Okay, thank you, sir.
Any more questions? So better to clarify. This is actually a discussion class where you ask questions and we will. Yeah, you can ask the question now. You can unmute and ask the question. What is the question you have? For the benefit of all the people, you can ask the question. Love. You can get, I think you can see it from these chats. If you have a question, you can put it into the chat box. So then we will read it later, right? Right, okay, he just joined, right? Okay, so let's move on to session 2. We have already taken about 40 minutes, so we'll have to be rushed now. But anyway, important thing is to get the fundamental basic concept right. We should know oxidation number, coordination number, and the geometry of compounds, right? To start with. So this is a nomenclature you learn during A-levels. So I'm not going to emphasize much more. There are some rules and which applies here. The only major difference actually now recently during A-level we put names chlorido and chloro, also we accept them, right? Hydrido or hydro. So not to worry about that. You write whatever the form, we will be giving marks for both cases, right? But look at the ammonia, we call it amine, and we call it carbonyl here, right? We will come, it's all given in the book. If you look at the session 2, the information is given here. Nomenclature of, in page 19, simple organic compounds, simple inorganic compounds, and the coordination compounds, where we talk about neutral complexes, cation complexes, anion complexes. So we are given in page 20 the chart. There we have given Cl minus chloro, but somebody writes chlorido is also right. I think now recently we are using chlorido rather than chloro, right? So you have to remember that we will not penalize you for writing what is given in the book. So you do marks. F minus means chlorido normally now, but fluoro also accepted, right? And then we have the IUPAC nomenclature given here. And if you must go through, there are about how many pages? About up to page 25, about pages 26 we have session 2. So I'll go through now briefly. Rule 1, the oxidation number of a donor atom of a ligand is equal to the charge on it, right? Some are neutral, some are anionic. So there's a charge here. The oxidation number of the neutral donors or ligand is 0. There's no charge here. Ammonia is a neutral ligand, so there's no charge. Carbon monoxide, or we call carbonyl in this sense, nomenclature, there's no charge. Monoanionic, remember, mono means one, anionic, there's only one negative charge. Ligands have the oxidation number -1. So fluorochlorobromine things, -1 here. The sum of all the oxidation numbers of the constituents of the complex is equal to the charge of the complex. When you are writing a complex, you should have square brackets, 2 square brackets, and then you write them in the order. Normally you write the metal center, and most of the time you write the negative ions first and then neutral ones. Now in this particular case, the metal center is platinum, methyl is negatively charged in the ionic concept, cyanide negative, nitro negative, En means ethylene diamine is a neutral one with 2 nitrogen donors, and the phosphine is a monodentate ligand with phosphorus coordinating here. Normally we write the coordinating atom first, right? Here this is a shortened form, so we put it En, right? Now look at that. With outside the square bracket, we have a plus sign. So this is a cation. This complex ion here, cation here. So if you have a negative ion, we call anionic or anionic compound or an anionic complex. And to balance out, there should be always a negative side here. So might be plus Cl minus. That's the way we have right now. This we have given part of a complex, cation part, like sodium chloride. We have written the sodium plus here, but the Cl minus somewhere there we have not included. It might be very simple anion here. So we have the rule number 2, the sum, all that is equal to the charge on the complex. So if you add up, now in this case, methyl is -1, cyanide is -1, NO2 is -1, here 0, 0. Now to get something out +1, there are 3 negatives. So you need to have 4 plus here. 4 plus, 3 negative cancelled out, ultimately end up with 1 plus. Is it clear? That's the way. No need to write all this. You are not getting marks for these things. This is some sort of clarification for you to know. We don't need this. Some people will write this. We are not going to get pass marks for writing these things. Remember, if you ask what is the oxidation number, you can put it here -1, -1, -1, 0, 0 to get that 1 plus. If you put it 4 plus, that is good enough, right? Rather than writing all this. So we'll be wasting your time writing all that. No need to write that. So we are not giving any pass marks for that. Only thing we are right now here, methyl, you can put it -1 here. It's an ionic one, ionic. Whole thing depends on there are 2 models. We got ionic model and Cow-Weller model, right? So here, if you go by ionic model, then only we become 4 plus. Here 4 plus. Ultimately, you get the. Now this is some sort of breakdown for you to think how you got it. But normally, don't waste time writing these. Is it clear now? We go to the next one. So, when naming a salt, first name the cation, then the anion. The oxidation number state of the central atom or ion is shown by Roman numeral in brackets immediately after the thing. So let's take this compound. But it's very known, you learn it during A level. Still a compounds with 2 ammonia and 1 bromo. So you name the ligands first. Amines. And there are 2 of them, you call diamine, and it's called silver. And the oxidation state of the metal is going to be +1. Here you have -Br. So we call it bromine. So what you learn during A level applies here. We cannot change dates. There are 680 people waiting for this exam on that day. So you better change your practical class, right? There's no way of putting it out. For the benefit of one person, changing 680 pages might be ridiculous, right? So you should ask, don't ask silly question from me. Right. So when naming a complex or molecule and the name of the ligand, first in the alphabetic order, regardless of their charge, then write the name of the metals followed by the oxidation number of the metal. So the same thing what we discussed earlier. Now we have more ligands. The nickel is center. We have Cl minus, Br minus, ammonia 0, carbon monoxide 0. Now this is square bracket. When you're looking at that one, there is no charge after the square bracket. So therefore, there are two negative charges. That means nickel is 2+. Balanced out nicely. There's nothing outside the square bracket. So there are two negative charges. So got to be nickel 2+. That's the oxidation number of nickel. So you can calculate that immediately. No need to write all that Cl and Br minus and all that. Then naming, you look at the alphabetical order. Ammonia means we call it amine. Remember, there are two M's. Amine with two M's. Then A alphabetic order, then you get bromo, and then you get carbonyl, and then you get chloro. Here carbonyl Ca, here chloro CH. Right? So the nickel is the one. Right? The complex negative ions end up in 8. So ultimately you have ATE at the end. Syncate. Not just zinc, syncate. It indicates we have anionic salt here. This complex part is anion, right? Complex negative ions. So actually it is anion. We can have Cl2 here or something else, right? Now we have to have sodium something here to cationic something. So there are 4 of them, tetrachloro, syncate 2. And in this case, tetrabromo, chyprate, ATE, oxidation number 2. So likewise, actually, you go through the book and you will find more of the examples. Since we have only 2 hours to go all these sessions. So remember, I just touch on now. If there are more than one, you call it di, tri, tetra, or pentahexa. Now in this particular case, we call it triamine with double M, right? And then 3 of them, trichloro. And when you are numbering these or naming, we ignore this number and on the C and A and that one. I mean 3 ammonia, right? And when naming, it's there, right? So you can go on all that, and the prefixes are disregarded when alphabetizing the ligands. Bridging ligands are used, right? Better go through the book for the session 2. You will find more examples, and there are questions after that, and there are some study questions also, right? So anything not really particularly not clear, you can ask now. Session 2. IUPAC name. You please mute yourself, right? Okay. I think we'll move on to the next session. Please.
Sir, excuse me, sir.
Yeah.
Sir,
Yeah.
sorry. So, sir, from the previous slide, if we use chloride or instead of chloro, is it wrong?
It's wrong. A name of a ligand within the bracket should end up with O all the time.
Okay, sir.
Chlorido, chlorido, or chloro.
Okay.
When it's an anion, you end up with chloride, right? If you go back now,
Oh, yes, sir.
for example, if we had a Cl minus here, so we call it chloride. After writing all that name, this part, we say chloride. For that Cl here, right? Like sodium chloride, cation first, then anion. You write anion later, then you can put it chloride, okay? So within the bracket, if there's something inside this bracket, it is coordinated. So there you put chloro or bromo, end up with O, oxo, right? Or chlorido, bromido or something, right? Any more questions?
No, sir, thank you.
MRC, what is that for? I just joined
Yeah,
now.
fine. Okay.
So how many people are here? Not that people, it's not bad.
There was 160. I recorded that.
So we'll move on to the next one. Session 3. Now we finished nomenclature. The next one actually isomers. When you look at the carbon chemistry, there are few isomers. We call it cis trans and that other constitutional isomers. Now here we have ligands and there we have metal centers, so we can have more isomers. But we just briefly go through this now. Isomerism in coordination compound, and there are few cases what we can say. Ionization isomerism. Ionization isomers have same empirical formula, same number of carbon, nitrogen, oxygen here, like here given here. But when you dissolve it, you get different ions. For example, if you have a salt here, there may be 2+ here, and then you have sulfate 2-. But you can put this sulfate inside, and you can get the chloride out. When you dissolve, you have a chloride ion here. Sulfate coordinated to the cobalt cell. So it's a complex cation there. And here, when in a water solution, one contains Cl-, one contains sulfate. That's the main difference, right? So ionization isomers have the same empirical formula, same formula, same number of carbon, nitrogen, and cobalt, metal, all that stuff, but differ in the coordination anion, thus yielding different ions when dissolved in the solution, right? Right? Hydrate isomerism, actually, instead of that, we have a water as a coordinating atom, and also this. Now say, this is an analog of ionization isomer, except the water molecules or a neutral ligand. Earlier we have an anionic ligand. Yeah, anionic ligand, two anionic ligands. In dissolving, we have 2 different ions. Now here, all the neutral ligand is there, replacing an anion ligand. Right? Earlier 2 anionic ones. Here we have 1 neutral one and 1 anionic one. So for example, 3 different chromium 3+, oxidation number is 3+, compound with the composition. So we have the same composition. There are 6 water molecules and 3 Cl ions, right? So when you have this compound and it contains 3 chloride ions, here we have 2 chloride ions, here we have 1 chloride ion. So depending on that, and we call there different colors. So these are the hydrate isomers. So earlier we put sulfur inside and we took 1 Cl out. Now in this case, we are putting chlorides in and get water out. So then we get 1 out, we get 2 out. So we call this coordinated water, hydrated water. They are packed in the crystal structure. So this is the complex. So look at the coordination number. Here coordination number 6. Here also coordination number is 6. Here also coordination number 6. But we have different number of chloride ions and will result in different colors as well. So you can say 3 chloride ions, 2, right? So these are the hydrate isomerism. Some example, you can put it some different metal centers can have. The coordination isomerism. For example, in this case, both cation and anions are metal complexes. So both cases, now here only cation complex. Anion is not a complex here. So when you have a complex 2 cations and anions, there are different combinations. And it could be more complex, but you better read it. And now here in this particular case, ammonia with cobalt here. And cyanides are with chromium. The other case, we have cobalt with cyanide and chromium with ammonia. It's complete outside. But you can have partial ones as well. So it's going to be more complex one. At the moment, we can think about changing the anion and neutral ligands only. One containing one type of anion. So therefore, in this case, chromium case, we are having anions. Here, cobalt is having anions. So there are different possibilities. So I'll go to the next one. There are bridging ones. Coordination, position isomerism. If you look at everything is same. Now, cobalt containing 4 ammonia and other compound cobalt containing 2 and 2. Now here it's balanced. There are Cl and 1 Cl and ammonia 3. So this is more like a symmetrical molecule. This is asymmetrical, but they are 2 different compounds and they have same composition. They have same number of chlorine, ammonia, and all that same, right? But the position, coordination position will change. Now here this cobalt get only ammonia. Here cobalt get ammonia and chloride, right? And the bridging ones also same. So likewise, you will be getting different isomerism. I'm not going to go into more detail now. The other one is called linkage. Now, there are ambidentate ligands. Ambidentate means it can join two different ways. For example, we'll take the example here. NO2 can join with nitrogen or oxygen. So ambidentate means nitro group can be oxygen coordinated or nitrogen coordinated. Depending on that, there will be different colors. So there are two different compounds. When you look at the exchange structure, we notice that nitrogen is coordinated. And here we have oxygen coordinated. Rather than going to all this, just briefly, and you can see that from the color, one is yellow, the other one is red, right? So then, polymerization isomerism, actually that is not really isomerism, but you can see composition is going to be same. Now here, platinum, chloride, ammonia 2. Here we have the same 2 platinums and 4 ammonia and 4 chloride. But the polymeric means here 1, 2, 3 like that, but they are not real polymers. But if you look at there's a pattern each time monomer and 2 of them, 3 of them, and 4 of them, right? So that's what the idea is actually. Polymerization isomerism. Then geometric isomerism we have here given, like what you learn from organic chemistry, cis form, and is particularly appear with the square planar ones. You won't see this thing in tetrahedral. Coordination number is 4, but you won't see. Square planar one, you have to draw nicely, straight line here, straight line here. A is trans to B. A is trans to B. 2 A's are cis. We have to take only the 2. Important one is the 2 number. 2 is cis. And here 2 A's are trans. And if you look at the octahedral compound, we look at the 2 of them. Now there are B2 only. B2 cis. Here B2 trans. Forget about the other ones. The 2 number is cis and trans. We are talking about cis and trans. We are talking about only 2 things. 2 things of the same kind. 2 atoms the same. So they are cis and they are trans. When you go to FAC and MER, we are looking at 3 atoms with same kind. So some people get it wrong. They always write cis and trans or FAC and MER without looking at. If you are talking about cis, there should be 2 of same kind. If you are talking about FAC and MER, there are 3 of same kind. Right? That you have to be remembered, right? Now, if you look at further down, trisubstitute. Here now we are getting fact A3B3 or even A3B2C or A3BCD, like whatever the combination, there are 3 of them with 1 prime. So in that case, you can have fact isomer, which means these things in one phase. There is a triangle can be formed here. We call deltahedron. So all 3 in same phase. That's called facial. And the other ones are going to be trans to each of these cases, right? Now in the other form, MER, they are in one plane. 3 A's in one plane, and the other plane we have B3. So they are perpendicular. This plane is perpendicular to that plane. So A3, B3 can have that. So these are the major difference. If you talk about FAC and MER, which means there are 3 of ligands with the same kind. So if you look at the optical isomerism, we learned that in organic chemistry, you have to look at the mirror image. If you look at the mirror image, and if you can superimpose them, they are not optical isomers. They are not optical isomers. If you look, for example, this one with the complex octahedral compound. Now we have molybdenum here. There are 3 carbonyl, right? And if you look at the mirror image, if you push it round here, what you are going to get in this particular isomer, this nitrogen is coordinated to this. So you have that and that. Now here we have that. So this is going to that. So they are not going to superimpose. These carbonyls are same, but that nitrogen is, there's a CH2 here, right? This NH2 here, right? So this NH2 will go here and end up with here, and this will end up with here, right? So you have to imagine a little bit. Now, for example, the square planar complexes, if it is an optically active ligand here, now if you take the mirror image, this methyl is up here, methyl, and this H is mirror image down here. And if you push this round here, And what you are going to get, this MEH will end up with here, ME top here, and it's down here at this position, not this position. But if you fall over that way, this compound will have methyl down and H up. So if you fill it, turn it round, you want to get the same compound. There are two different compounds, looks very similar, but they are enantiomers. So likewise, always take the mirror image and see whether you can superimpose them. And if they are not, they are enantiomers, right? So if you have a plane, that means there is no plane of symmetry here. If you look at that plane, Cl and this plane, one methyl is up, one is H. If you have H's only, superimposable, so there is a plane of symmetry. If there's H and H here, they are optically inactive. Then you get the same thing, right? Even this case, if you remove these bonds, if you make ammonia here, that's a plane of symmetry. If you have only ammonia here without these bonds, because the bonds make it optically active here, coming here or the other way. If you have only ammonia, they are superimposable, so they are optically inactive. So I'm going to go down here. This is a good example of what you learn in organic chemistry. There are 4 different groups joined to a carbon atom, and if you get the mirror image, they are not going to superimpose. You can turn it nice, you can bring this B here, and A will be there. Now you will switch now. Now you have a D here and C here. They are not superimposable, but they are for tetrahedral geometry. Now we mentioned that octahedral compounds can have optical isomers, and star planar complexes can have star planar, and even the triple compound simple ones have star planar geometry, right? So these actually, again, you can find them. So any question from the audience now? Isomerism. So we have page 27, right? Page 29, and then linkage isomerism in page 30. Then polymerization in page 31. Then we have geometric isomers, cis and transform we discuss here. Right? Then Kapkan mentioned here. Optical isomerism in page 33. Right? So up to page 37. We have any question from you? There are so many chat box. I don't know whether we can answer all of them now. So they are just joined. I don't know whatever, but there aren't any. I don't know. They are not really questions, right? Message.
Excuse me, sir.
Yeah.
Can you please briefly once again explain only the optical isomerism, sir, please?
Yeah. Optical isomer. Now let's take this particular one, square planar complex. If there's CH2, both are HS. You can have a plane of symmetry. If you have a plane, then there's symmetry here. This plane, and now since introducing a chiral center here, just introducing a chiral center here, becomes they are optically active. So if you take this compound and flip over here, then top methyl will end up with here, and then H will end up with here. The rest is same, right? So therefore these are 2 different compounds. When you take the mirror image, and the resulting compound is different to the initial compound, and they are optical isomers. Even same thing here, if you draw it, if you try to fix this around here, this isomer means you have a bond between here to this nitrogen, and this will be NH2. So they are not superimposable. So therefore, they are optical isomers. And here even the same thing, tetrahedral. This is the mirror image. You can turn this one from here to here, we get the B here. Then what happens? That D will come and sit here. So C become D here, and this C become here D. So therefore, they are not superimposable. But you learn during A level and even organic chemistry, if a carbon center is linked to 4 different atoms, they are optically isomers. Is it okay now?
Yes, sir. Thank you very much, sir.
Okay. So we'll move on and see Session 4. So there are 5 more to go. Session 4, roughly about bonding. We talk about metal centers, then we talk about ligands. Very briefly look at how they join together. So we call it the first, the ligand donates a pair of electrons to a metal, forming a sigma bond. We call it sigma. These ligands are known as sigma donors, or also called Lewis bases. Normally, we know if you take ammonia for an example, ammonia got lone pair. That lone pair is donated to a vacant orbital in the metal center, forming a sigma bond. We call it a sigma bond. So we call Lewis bases. Some ligands contain empty orbitals which can accept electron from the metal, forming a pi bond. We call here P means pi bond, right? So ligand gives electrons, lone pair electrons, and make a sigma bond. Now, when a metal center has more electrons, it's not very stable. It just wants to get rid of some of the electrons. So what it does, it donates back some of the electron density to a vacant orbital in the ligand and making a pi bond. So therefore, there are 2 more, more like a double bond now, and it makes this complex stable. So metal giving electrons to the ligand, there should be a suitable energy, energetic orbital to accept it. For example, carbon monoxide, there are pi star orbital which is willing to take electron density from metal to that carbon monoxide. So therefore, there will be a shorter bond, giving this way and that way, ligand come closer to the metal, so making more stable bond. So that's called pi bonding, and we call it ligand is pi acceptor. Here we call it sigma donor. This is called back donation. We are giving back. Metal is getting first, and it's giving back some of it or some of the density. So we call back donation, which results in back bonding. And back bonding reduces the separation charge. Electron density is reduced from here, the metal. These ligands accept electron density from metal centers are called pi acceptor. We have introduced 2 terms now: sigma donor, pi acceptor ligand. For example, if you take ammonia, nitrogen doesn't have a suitable energy to accept electron density from metal. So therefore, there is no pi bond in ammonia. Ammonia is just a sigma donor only. But if the phosphine case, it takes up some of them from metal center to make a pi bond. For example, if you have 3 fluorines here, so it's removing electron from phosphorus, so metal can give more electrons. If phosphorus is getting more electron from substituent, it can give a better sigma donor, but doesn't want to accept electron from the metal sector. So therefore, pi acceptability, sigma donor ability depends on the substituent on the coordinating atom. So this is the way A level you draw it. You put a coordinate bond here, lone pair here, so they are same way. Rather than putting arrows, you can make the same bonds. There are 4 bonds. And now here, what is the oxidation number of cobalt here? Can you answer now? What is the oxidation number of cobalt, copper here? You have Cu. What is the oxidation number here? +2, right? +2 plus, because we have 2 minus here. So whole thing is neutral now after that. So therefore 2 plus. And what is the coordination number here? Copper. Coordination number? 4. So there are 4 links. There are 4 links means coordination number is 4. Oxidation number is 2. And this is a salt now. Remember, it's like a sodium chloride. It's a salt. There are 2. When you dissolve this thing, you can see chloride ions in the solution. Right? So that information you have to remember. And now you should know what is the group number of copper. Group number. At least look at the book and see. Oh, table even wherever you can remember, you have mentioned earlier. You add the number of D and S electrons. As you remember the first series, group number
12.
12. So what is the page you are adding? So it's 12, right? Remember at least. So what is the group number of palladium now? Or cobalt? What is the group number of cobalt? Group number of cobalt here. Right now here this we have copper. What is the group number? It's given in the book. You can see it from the book immediately. Not only book, we have the cover. That's what I said. If you know the cover, you might get 40 marks straight away. Look at the cover. It's given here. Don't have to look for anything else. What is the group number of cobalt? Look at the cover page. When you are traveling, you look at the cover page. Huh?
9.
9. So everybody should look at the cover page now and at least remember the group number. What is the group number? 9 and so on. What is the group number of chromium?
It's 6.
6. Now remember now, chromium, molybdenum, and so on. Tungsten. At least you can remember the group 6 metals. So there are 3 metals which are important. Chromium, molybdenum, and tungsten. So right. The next step is, so look at the group number here and see the group, right? Okay, now we'll come back to the lesson. So the bonding in coordination compounds. Right now we go down further and it says primary valency. Actually, I must make it short now since we are running out of time. Primary valency is equal to the oxidation number. Now here in this case, oxidation number cobalt is 3, the primary valency and the oxidation number is same. Here the secondary valency comes with the coordination number. Here in this particular case, this cobalt center got 6 ammonia ligand. So the coordination number is going to be 6. So 6. So I must rush it now, otherwise I won't be able to finish all that, right? Now that is important when you are looking at a cobalt amine complexes where octahedral geometry. If you mixing cobalt and ammonia in the chloride form, you might be getting different compositions. And this is the form you get. But if you look at now, in this particular case, there are 3 chlorines and 6 ammonia. You can have this sort of compound being formed. But if you look at the number of X means number of chloride ions precipitated as silver chloride. Now here we have 3 chlorides. So you can precipitate them as silver chloride. You dissolve it in at silver nitrate. This is going to be precipitated. So then there are more ions in the solution. So therefore, the conductivity is higher. You have a solvent, water soluble solution, more ions. The conductivity is equal to something 400 something. The number of ions, 3 chlorides, and the complex cation make it 4. So likewise, if you go down, even this particular case also there are 4 ions, 3 chlorides and that cation. And here we have only 3 ions, 2 chlorides and the complex cation. And here we have 1 ion, cation, anion and cation. We call 1-to-1 electrolyte. And here no ions here. It's a neutral compound all inside the coordination sphere. Everything is a coordination sphere, nothing outside. So this is we won't see any conductivity. So some idea I should have. If it is around 400 or something, there are 3 ions or 4 ions in the solution, right? And if it is 250, there are 3 ions in the solution. If it is 1-to-1, you have 100. So if you have a rough idea and what I'm going to get from the coordination number and oxidation number, you should be able to look at the composition. All these compounds got coordination number 6. So they are octahedral compound with different number of ammonia and chloride composition. All these cases have only 3 chlorides. and some of them are got different types of different amount of ammonia. So is it clear now? The conductivity measurement will tell you whether it is the 1-to-1 salt or 1-to-2 salt or 1-to-3 salt. If it is around 400 something or above, there should be 1-to-3 salt, right? Total number of ions going to be 4, right? I'll move on quickly. So this is example given for you to work out nicely, right? And effective atomic number, there's another rule called effective atomic number. Here, now here, suggested that electron pairs of the ligand can be added to the central atom and it has become the next Nobel Prize. If you have metal center, it will take as much as possible number of electrons to reach the next Nobel gas. That is the theory behind. So we have to calculate the total number of electrons in the central metal atom, including those gained from ligands, is called the effective atomic number. Metal got some electrons, and the donated by ligands we adopt something, and the total is called effective atomic number of the central atom. In many cases, it is equal to the atomic number, we said, of the next one. Don't get, for example, 36 or 18 and so on. Now, for example, we just work out this one. We have a cobalt compound with 6 ammonia and it is positively charged 3+. So the oxidation number here, cobalt is going to be 3+, and the coordination number will be 6. So now you can see number of electrons, cobalt 0 valent cobalt, Z number is 27. And the number of electrons when it is oxidized, you remove 3 electrons, -3, 24. Each ammonia, the nitrogen giving lone pair, so 2 into 6, 6 of them, 12. And then add up all of that, 24 that, we get 36. It is so more stable. Now here, coordinatively saturated compound. It's all filled. So that's the way to calculate that one. We have given some simple equation for you to calculate so that you can use. I'm not going to go through this table, right? This is the way to remember. En is equal to atomic number, or Z minus coordination number, oxidation number, and then plus 2 into coordination number. So that is the each coordinating atom is giving 2. That's what there are 6, 12. That's what we got earlier. And the cobalt case, we have removed 3 of them. So you can use this one. Make sure you write the correct equation before you do the calculation. Sometimes people use minus here, sometimes people use plus here, so they can't remember what's happening. If you work out with the normal way, which I showed you, might be easier, but this is an easy way of remembering. So check with your answer, right? I'm not going to all these tables. I won't be able to finish now. Another half an hour left. Now, if you look at this, right? So this table, we have it here in the page 43. So you look at that page, Z number is giving, oxidation number is giving. Now you should be able to calculate all that. The number of electrons donated by ligands also given 12, 12, 12, 10, 9, that depending on the number of ligands. Here we have 4 carbon monoxide giving only 8. Oxidation number going to be nickel 0, 0. And the Z value is 28. So when you add up that one, but 30. So they are coordinating, what do you call this? We call it, it fulfills the EA. If it is less than or more than that, it doesn't obey, right? That's what you have to remember. I'm not going to go into more details here. If I go down now. So these are the coordination number and the orbitals involved in the hybridization, right? So we call it valence bond theory here. And I must say, if you want to look at what you call SPD blocks, we have put some OER. I think you should go visit our OER section. There you can give more clear explanation of the 3D elements and S-blocks elements and all that. On top of that, we have included, we have a called chemistry digital room. If you go to library site and look at that, digital OER and also digital room chemistry, we have given some simple forms of these lessons. CFT, isomerism, which was related to this one. We have information there. So go and visit that, and you should be able to see sometime very simple. All right. And one other important thing, actually, better try all the MCQs given in the learn all yourself. Lesson wise, or the what you call book wise. We have to unit 1, 25 MCQs. You try your yourself and find the answer. That will be a good practice for that 15 MCQs. But for writing the answers, you have to go and do the book. Do the book and try past papers. You go to our site, we have given the information where to get past papers. Even Dr. Paukila has put most of the past papers there. So better you go and try yourself. Only thing you have to practice. Practice makes you perfect. So exam time, only 1 hour. You can't play with most of the things. You have to quickly understand it and get the answer. So there is a written part as well, right? You won't be able to copy from anybody else. You have to do it here. So you can see somebody is getting copied MCQs, right? But he doesn't know anything about the written part. You write the name there nicely, MCQ tick nicely, that can't write the nomenclature. So we will check on that one. So better spend some time and do all the MCQs given in the book, the book as well. There are at the end we have study questions and some MCQs and written ones, and I'll try to do them next time. Next day school, the next one. I'll go through the MCQs given in this book, right? So now you have to try out them. You try out them, and I'll ask questions and see how people will have done it. You cannot do recording, right? We'll do the recording. So please go and do the MCQs given on the study questions. That will help you to improve your knowledge definitely and work out all the activities given here. Try yourself, right? Right. So these are the orbitals involved in coordination number 2. They are going to be SP, 4S, 4P. They are linear. We mentioned earlier. So in the case of coordination number 3, there are 3 orbitals involved, 4S and 4P, right? 2 of them, right? So we can go through that information probably given in the book, right? In page 46, right? So there are 2 orbitals and here 3 orbitals, 1s and 2p's, right? Trigonal planar, an example is given. Now tetrahedral case, there should be 4 orbitals involved and 4s and 3 of the p orbitals, right? And star planar, the orbital involved in hybridization, DSP2, remember, not SP2D, right? Right, you have to remember that, DSP2, right? And in the case of coordination number 5, this is for tetrahedral SP3, star planar we have DSP2, and coordination number 5, there are 2 possibilities, DSP3, SP3D, right? You can remember all that. I'm going to move on to the next one. And what is given here, nature of bonding. So valence bond theory is briefly touched on here, I think. There are some assumptions you have to make. The central metal atom or ion makes available, we mentioned about the orbitals here, available number of empty SPD orbitals equal to the coordination number, right? Then they hybridize and then form hybridized orbitals, and they are the same, degenerate same energy, right? And the ligands have at least 1 orbital containing a pair of electrons. Each ligand, the donor atom, should have a pair of electrons for the donation to take place. And then the vacant hybrid orbitals of the metal atom overlap with the filled orbitals of the ligand to form, right? So that's the assumption. So if you take a example here for the valence bond theory of octahedral compounds, let's consider cobalt-3, and we have fluorides, 3 minus because fluorine is -1. There are 6 of them. Oxidation number is 3 plus, so 3 minus out, has 4 unpaired electrons. So cobalt 0, S2, D7, the group number is 9 here nicely, adding up these 2, 9. And then if you make cobalt 3+, you have 6 left. We remove 3 of them. It's called D9. This D9. And now here, that's a group 9. And then you have 3 Ds. So when you are going to have 3D, 4S, 4P, 4D, you have filled electrons trying to be unpaired as much as possible, right? So in this case, we have 6 electrons, 5 here, and 1 paired electron. And now, metal center should decide, now 6 orbitals to be picked. Now picked up these 4s, 3 of the p orbitals, and 2 of them, and hybridized sp3d. That's the way we have put earlier case. How you get sp3d. Octahedral case, we have sp3d orbital, and that is what we got. And this is the same thing we have mentioned. sp3. The number that we have drawn is coming from here. But if they are paired here, if they are paired, you can use this 3 vacant d orbit. Then you get d2sp3. And this is where, in this particular case, they are unpaired. We look at the magnetic property, we know this particular compound get 4 unpaired electrons. Sometimes they all are paired, so then we can have 6 of them paired. So there will be 2 vacant orbitals. In that sense, we get d2sp3 hybridization. We call this one outer orbital case, and when you paired it, we call inner orbital. So there are some names for you to remember. So that's actually basically you have to decide. Metal will have got to decide how many orbitals to be used depending on the coordination number. They are going to hybridize and generate things. So now these vacant orbitals are filled with fluoride ions 2, 2, 2, 2. So that's what we have. If you have the valence bond theory, this is the concept. That's a very weak theory. This cannot explain magnetic properties and so on. But this is the initial theory, like organic chemistry. When you have done organic chemistry, we talk about carbon, sp3 carbon, sp2 carbon. So people, when they notice they are metal complex, they also apply the same thing, but without much success there. But the later we got the valence crystal field theory, and after that we got the molecular orbital theory. They are more complete, more explainable, right? So we're going to move on to the next one. Next, I'm going to skip all that. Otherwise, we won't be able to do much. Tetrahedral complex. So you look at the same thing. How we are going to hybridize, right? D5. They are filled nicely. So the sp3 hybridization here we end up with here, right? Very similar. We can go through stereoplanar complexes where we notice normally D8 they try to depending on the type of the ligand. Cyano is a strong ligand, so normally you get paired here. Otherwise, you get sp3, what you call sp3-4 tetrahedral. But normally, observe is the other way around, which depends on the magnetic property. If you have a diamagnetic center, we need to get everything paired, no unpaired electrons. So the normal D8 compound is starplanar. We have DSP. I'm making the lesson short, right? You have to read and see how you argue there, right? So now this is so then orbital inequality here, because this particular compound is what you call diamagnetic. There aren't any unpaired electrons, right? So in this case, the hybridization is going to be DSP3, sp2, right? So the limitation of DBT, the color and the magnetic properties, the transmetal complex are due to the presence of the D electron. And the wave does not explain color or spectra of the transmetal. Read that one. That's we are in public page 49, and the limitation talk about page 50. Then we'll move to the next session, crystal field theory. There are 3 more sessions. So any question from that valence bond theory? If you look at the complex, there should be a metal, there should be a ligand. So you know coordination number, metal should select. number of vacant orbitals from all these, depending on the coordination number. And we'll have to get the information from somewhere else, whether this compound is diamagnetic or paramagnetic. Depending on that, we have to select inner orbital or outer orbital for the hybridization. That is the bottom line you have to remember, right? So thereby you might get DSP2 or this P2D type, right? So move on to the next session, session 5, crystal field theory, right? So normally we'll have to remember the shapes of the d orbitals. There are 5 d orbitals: dxy, yz, zx, dx squared, y squared, and dz squared. So we have given. This is a shape. There is x-axis and the y-axis. The electron density is located on these, right? We put minus signs, the plus signs here. So if you have metals, if it is a metal, a ligand coming from, they'll have a stronger interaction here, right? And this case, Pz squared, more interaction from here, right? And these, we call them, these two orbitals, we call them EG orbitals. And the nomenclature we call T2G for dxy, yz, zx, right? They are just two. They are located, the electron density located between the bonds. Here, along the axis of the ligand. The major difference between actually, there is a set where electron density, T2G orbitals having electron density between axes. So they are very similar. So they are same energy. And sometimes they can have more energy, right? Depending on the tetrahedral of particular octahedral geometry. So these are the chains. What we got to remember, there are 3 in one group called T2G. The other one is called EG. Now, next one. These 5D orbitals are not identical and are divided into 2 sets. And the shapes of dxy, yz, and zx orbitals are identical and they lie between the axes of x, y, z. These are collectively known as T2G orbitals. There are 3. When you talk about T2G, there are 3 orbitals. And the dx squared, y squared, and dz squared orbitals have different shapes, right? And point along the axis. And these are known as EG. In the absence of a ligand, when there aren't any ligands around, or the what you call naked metal center, the absence of ligand, the energy levels associated with all 5 d orbitals are identical. So they have, we got degenerate all 5 in one. When the ligands are coming with 6 different directions for an octahedral compound, they are having more electron density towards some of the orbitals, some are. So therefore, this energy going to differentiate split. So depending on EG and EG. So that varies with the octahedral geometry and tetrahedral geometry. That's what the CFT explains. This sort of splitting of d orbitals depending on the geometry. Even the square planar, that's another one, right? So that's what we are going to talk about in this case. Now there are some assumptions made in this assumption of the CFT. Ligands are treated as point charges. Earlier we looked at orbitals. Now here we are looking at the electrostatic forces. So therefore, they look at ligands as negative charge, metal center is positive charge. So there are some attraction, right? The bonding between the metal and the ligand is entirely electrostatic charge interactions, repulsion and attraction, right? There is no interaction between metal orbitals and ligand orbitals. So the different from the VBT, here we have excluded all that orbital interaction. It's not quite right. That's why the next theory, molecular orbital theory, going to involve in that orbital interactions as well. In the free metal atom, the d orbitals have the same energy. So they are degenerate if it is a free metal, means zero valent metal. Zero valent metal without any ligands around, all 5 are same. Right? So these are the basic assumptions. In octahedral and tetrahedral complexes, 6 and 4 ligands around the metal center, where ligands do not produce a spherically symmetrical field. Because metal center, if everything is same, that means there are so many ligands, you have a same effect. Now there are axes. And octahedral case, we have ligands coming along the axes. When in the tetrahedral case, they are coming in between. So there are major difference. Therefore, the splitting of the EG T2G will have a different effect. Some are strongly interacting, have higher energy, right? So we look at that. Ligands not produce symmetrical, and thus the d orbitals are no longer d. So they have a separate energy levels now, right? So this is the case for CFT for octahedral compound, right? So initially I mentioned free metal center, all 5 equivalent, but there is a similar field, spherical field is coming all the time. If it is the case, but we don't have spherical one, we have only located, isolated ligands. So then it's going to sit orbital of interactions with energy electron interaction. The energy level will be shifted up. Now, but after that, if you think about the octahedral field, some having more interaction, so they will be have higher energy. Along the axis, we have EG having higher energy and other EG level or T2G ones having a lower level. But the generation here and multiply by 2 and this gap multiply by 3 have the same. We have cancelled out. What is increased has to be cancelled out from what is. That's the idea you have to get. So we normally call it here plus 0.6 and plus 0.4, but multiply by 3 here multiply by 2. So in other words, this splitting of d orbital is caused by the redistribution of negative charge in the spherical. Now here we have spherical all surrounded by same energy or same electron cloud. But here we have isolated electron density. So therefore, now we'll have the spherical electron is not there. And octahedral field, the 6 negative charges on the axis, axis. This effect of splitting of d orbitals by the ligand field is known as crystal field. So we looked at the metal center, positively charged, and they are talking about ligands as negatively charged. Depending on the coordination number, we have different geometry. For the case of octahedral, we are going to have 6 ligands. So there will be 6 directions. Electron direction will be severe and the energy is raised. That's one, right? And the other orbitals, they are located in between the axes. So they have a small effect, so that they are more stable here. So these are energy increased. So the difference between energy T2G is called denoted by delta now. O means octahedral. O means octahedral. Delta means the name, the splitting. And that's also sometimes people say 10 BQ for them for you to calculate. Right? The delta represents the crystal field splitting and the subscript is O for octahedral. For tetrahedral, we call delta T. Octahedral case, we call delta O. Right? So in the tetrahedral case, it is different. Now we have more energy here, so they are up and they are going to be down. So we have T2G or up. Now here EG will be down, T2G will be up. Right? So now look at the total energy of the system cannot be altered during the redistribution. We have energy to redistribute it, like sp3. We have hybridization. We take 4 orbitals with different energy and hybridize get 1. So likewise, the total energy cannot be increased or reduced. Nice. So something gain should be compensated from somewhere else. So the total energy system cannot be altered during the redistribution of the charge and step 1 and 2. The total increase of the energy, Eg, equals to the total decrease in T2. Therefore, you can see now, here the baseline 0, and there are 2 orbitals, multiply by that, and 3 orbitals, multiply by that, will have cancelled out, reach the same. So the gap is here higher, gap is here smaller, because the ratio is going to be 2 to 3. So this is what now octahedral case stabilized by, here this is called 0.4. 2 divided by 5 is 0.4. Here we have 0.6. Ultimately, when you add up whole thing, it's going to be 0, right? This is what's given. Determine the d electron configuration of titanium in the octahedral complex. So titanium octahedral complex, the compound actually 3+. So oxidation number of titanium is 3+. Titanium is group 4. So we remove 3 electrons, it got only 1 electron. Titanium 3+ means it contains only 1 electron. So where does it? Now titanium 0, the group 4 metal, and 3+, only 1 d electron is left. So it should be located at octahedral compound. Now here it's octahedral compound. The splitting is going to be T2G and EG top. When it is coming here, normally you get energy here 0, but now it is stabilized. This electron is stabilized, but it's in a lower level. Earlier it was there, higher level. Now it is stabilized. So that is what we call crystal field stabilization energy for 1 electron is going to be -4. -0.4 delta, depending on the gap. That gap might be 100, might be 200, might be 300, but stable in 0.4 minus. Stabilized means minus. We have negative energy stabilized. Right? So the contains 1 d electron, 61 and octahedral geometry. D electron will occupy the T2G orbital. Electrons always prefer to occupy the orbital with the lowest energy. Therefore, d electron configuration according to CFT. Now we are talking about the CFT. We then write d electron configuration T2G1. Earlier you put it 1 electron, might be S1 or D1, right? S1 electron. Now we call it D1. Now we have to say CFT. It is the electron configuration T2G1. When you have 1 more electron here, the other metal centers or something, TD2G2. Here if you have another one, T2G3. Now when it comes to the 4 electrons, there's a decision to be made whether this 4th electron should go here or get paired. If this gap is so large, it has to get paired. If this gap is so small, it prefers to go up. So depending on that gap, crystal field stabilization will vary depending on the size of the crystal field splitting. If you have a stronger ligand like cyanide, the gap is so high. So it automatically pairs. If you look at something small fluoride, right? Their gap is so small, whether it is coming here or here, not going to happen. So that is what we are going to discuss later. Factors affecting the size of the crystal field. The size of the magnitude of the field is dependent upon the nature of ligand. Ligand again, nature of and the geometry of the complex, whether it is octahedral or star planar or tetrahedron, depending on the complex geometry, the splitting going to be different. And charge on the metal center might be 3+ or 2+. Whether the metal center is in the first, second, or third. So depending on 3D, 4D, and 5D, the stability and the fitting of these things is going to change. So if effects of ligands on crystal field theory, free splitting, right? Right. Delta depends on the field strength. I mentioned there are two types of ligands. Some are strong ligands, so having a large gap. There must be smaller gap here. So we call weak ligands. Depending on the strength of the ligand surrounding the metal. So ligands such as iodide, bromide, halides with a small crystal field. You can give the numbers are given there, right? Termed as weak field ligand. Similarly, the ligands which PN or cyanide, carbon monoxide with a large crystal field splitting, the term is strong field ligand. So therefore, we have put the names now: strong ligands or strong field ligands, or weak ligands or weak field ligands. So we'll have two sets now. Some actually the borderline case might be very difficult to mark it strong or not. Now, if you look at that one, you have values, strong fields. So these are the ligands with strong field: carbon monoxide, cyanide, phosphine, NO2 minus like. These ones are very strong. Iodide, bromide, and thiocyanates and things have a gap, smaller gap. Small gap. Cyanide and things have a larger. So in other words, you can show that one in this way. These are smaller ones like iodine. And we have here larger gap between these delta nodes. So that increasing, if you look at that is cyanide. A means is chloride. You can see another way of putting it. Energy increases, the gap energy increases depending on the chloride to cyanide. Okay. Now, if you look at that effect of central ion on the crystal field. The crystal field splitting delta naught of a ligand depends on the charge on the metal center. So higher the charge, higher the value. 2 plus, vanadium case 157, and the same D, now it's going to be D2, earlier D3, now it's increased. So splitting is increased when the charge of the metal ion is increased. The position of the metal in the group. For example, if you take the cobalt, palladium, platinum, cobalt means 3D, the gap is smaller, 4D large, 5D even large. The delta naught increases as you go down position of the metal center. Crystal field specialization energy CFSE. CFSE. For a metal ion with M electrons in T2G of level and N electrons in the T2G level. So we can write it. Here we have EGM, and T2GN. So T2G. So that's how we write it. And you can calculate for this one. This is for octahedral geometry. CFSE is equal. We mentioned that top part is plus 0.6. Bottom part is minus 0.4. So same thing I put here and delta. So that will give you some idea about the value. So any questions so far? We are on page 53 to up to page 60 or something, right? Even 61 also we have touched. So CFSC depends on the charge of the metal center, the group, and so many factors, right? And how to calculate that value, we have got, first you look at the geometry, and you know there are T2G and EG separations, and you have to put electrons onto that whatever chart or the orbitals. Then you can see starting from T2G bottom and EG up, right? And you can calculate the value, and we'll see next one. Now here we have a metal center. When the orbital with unpaired electrons, so the complex is paramagnetic. Most of the cases, actually most of the salts are paramagnetic. Always there is some unpaired electron. Therefore, they are paramagnetic. D8 cases, they are diamagnetic. For stop when it comes to they are diamagnetic. So for example, we say vanadium 3+. So the case is D2. Vanadium group 5, remove 3 electrons, you get D2. Now, octahedral geometry, you have T2G at the bottom, and here we have 0.4 minus separation, here 0.6 and here 0.4, and we can write it down when the 2 electrons are here, T2G2 and EG no electrons. And D3 case, there we have 3 unpaired ones, and EG level is also empty. So therefore, we have T2G3 and EG0. Right? When it comes to D4, we have a difference. The electron can be here or here. Now here paired, here unpaired. If the gap is smaller, that electron can go here. And the gap is so high, it prefers to swing or cancellation, or we can have it, right? So now here we have T2G3, EG1 in a weak field. And here we have T2G4, we are all 4 in 1, and then EG node. So that's the splitting. So you can do for any metal center, depending on the D2, D3, D5. So if you put D5, for a D5 case, you can have it here for the weak field. And the strong field, it will come here. Then D4 here, D5, D6. In the case of D6, weak field, you have 5 here, second one, last one coming here. So we have 2 unpaired electrons, 2 unpaired electrons. Number of unpaired electrons will be 4 there. Now here we have next case. It's going to come here because so strong field here, difficult to go and up and stay. So there will be 6 d electrons here. Then only there is no choice that go up. That's right. So now here we have T2G0 and EG. They probably are a little bit now. So go through that, and it's given in the book, right? These combinations. If the pairing energy is high, and then it gets high spin and weak field complexes, right? And the question here, calculate the CFSC of this particular compound and this. There are 4 electrons and a smaller gap or larger gap. So therefore, here spin paired to a certain extent, here it's not paired, right? Electron distribution, which configuration is more stable than the other. So you can calculate that one using delta node, and you can see T2G3 and EG1, you have this, and the other one here. So this is minus, here also minus, but here 1.6 minus is more stabilized. So likewise, you should be able to calculate that. So when you are going to have a total energy, you have to say how much energy is used up. When you are pairing, you have to do energy. Forcefully keep them together. So therefore, you have to add positive. Here, this one is negative energy. Here you have pairing energy is positive. The total number is going to be that. Pairing energy is a positive value, and delta node delta naught star here, and should be like, go through the book. I think everything is nicely explained now from crystal field theory. Probably not touch little bit. Same thing. Go to chapter 6. I think we'll quickly move on to 6. This tetrahedral case. This is chapter 6. Crystal field theory 2. Application of CFT. Now, remember now, EG is at a lower level and T2G is a higher level. Now you have 2 orbitals here. We have 3 orbitals. Now these values. Now earlier it was 0.4. Now it's become 0.6. And top part become 0.4. But that is positive value. So it's stabilized here. And the tetrahedral crystal field we call delta T. Delta T means tetrahedral. And it is roughly can equal to about half of the delta octahedral. And the exact value 4 divided by 9. Right? So that's something we got to remember. Delta T cap piece, tetrahedral case is smaller. Octahedral case quite large, double the size. That we have to remember, right? Rough idea for anything which is larger. Delta naught is larger. So it says some of the, there I can see, basically closer to half, but the value, exact value is 9 upon 4. Now, if you look at normally half filled and filled. In D0, no orbitals, no electrons, and D5 half filled, everything filling 1 electron, and D10, everything is paired now. In those arrangement, CFS is going to be 0. There's no special stabilization. They are as normal as before. So 0 for both octahedral and tetrahedral. For all other configurations, the octahedral CFSC is greater than the tetrahedral CFSC. So delta value is larger for octahedral. They are more stable. Octahedral compounds are less stable compared to the other one. Crystal field stabilization is more here. Right? More stable than. So tetrahedral complexes are favored when there are large bulky group because of they cannot have the scarp geometry. They keep away from each other. So the better way actually have the tetrahedral. All ligands have equal distance away. Scarp plane, they are in 90 degrees, but top and bottom there's no what you call ligands. Right? And the ligands are weak field where delta T is quite small. The electronic configuration of the metal D0, D5, D10s, and there is no CFT. It's cancelled out. Stabilization is cancelled out from the other part. Therefore, no CFT. Ionic radii provide evidence for this crystallization. So this is for star planar compounds. Now, if you convert this octahedral compound to what you call star planar one, you got to remove these 2 ligands. Axial one, if you remove them, you get star planar geometry. So we know if you take the octahedral geometry, T2G more stabilized than EG. Now, when you remove that, removing these 2, what happens? That EG orbitals, D squared, Y squared, having large electron impact here, star planar complex, so energy increase here. And similar compensated by the one coming down. Even these cases, DXYZ in the same plane have higher interactions or repulsions, so it is increased energy, and this 2-1 should be equal to sin. So these Y, XY and DZ sometimes will have different arrangement. Sometimes DXY might be below DZ square. But what we know actually, dx squared y squared is the top one. Highest energy will have with these ones. And these on the xy plane, these orbitals have the low square plane. And roughly the value is about 1.3 times. So delta SP, this value is larger. So more stabilization here, and it's about 1.3 delta, right? And generally, a situation in an octahedral complex where two trans ligands are at a different distance from the metal center, right? And although we think there are 6 ligands around, we expect the bond length should be same, but it's not the case. Sometimes the axial bonds are longer. Sometimes these equatorial ones are longer. It depends on the symmetry of the electron configuration and the other factors. So that's what we call tetragonal distortion, right? Probably now nearly 3. And what are the symmetrical ones? If you have symmetrical arrangements of that one, D node, nothing there. So they are symmetrical. D3, right, is half filled here. So that's also symmetrical. And when you have D5, T2, G3 bottom half filled and EG fully filled, only the, so also symmetrical. D6, in the case of strong field, the gap is higher, all electrons are in the T2 given. That's also given. The bottom part is fully filled. D8 case, there are 6 electrons in the bottom one and EG, right? So these are the symmetrical electron distributions. Some examples are given here. Now, the magnetic properties of transsymmetric complexes, paramagnetic and diamagnetic nature. Spins are, right, paramagnetic complex with the unpaired electrons. If there are unpaired electrons, they are called, there is a magnetic moment, and they are paramagnetic, and we'll get a value for that. Magnetic moment, the electron rise upon 2 factors, spin of the electron, it is on axis or orbital angular momentum, and then people have found a relationship between these US. Spin only value is number of electrons, unpaired electrons, n into n plus 2. Now remember, sometimes people write n plus 1 for more reason, but remember it is n plus 2 and everything square root, and the units come with Bohr magnetron. So it's that important to write the unit. When you are writing a value, if you say 2, doesn't mean anything to anybody, but if you say 2 magnetron or Bohr magnetron, then we know that. So therefore, when you are going to calculate the mu s value, you can use this equation and you apply. Now in the top cases, we have number of electrons in one. Now here, there are unpaired electrons, there are 4 of them. So n value going to be 4 here. So n plus 2 going to be 6. So they multiply both them and then get the square root to get the mu s value. Now here also, unpaired electrons 2. So n plus 2 going to be 4. 4 into 2 going to be 6. 4 into 2 going to be 8. Then you are going to get the square root of 8. So you can get the calculation. Depending on this gaps, you can see the what you call mu s value. So I go down quickly. There are some spectra. You can see color of some of the compound. Why are some complex are white, some are colored and black? If the complex absorb whole white energy, it absorb everything, it appears black. Black surface means absorb everything, nothing is reflected. And if a complex reflects or transmits whole of the light, it becomes white. And if you absorb part of it, you can see the rest, or the what you call the word actually complementary color. That's what I remember. And some what you call, there are transition. You get colors due to transition. Right? And DD spectra transitions are not allowed. So you have sometimes the same d orbital. If you are going from S to P or different levels, they are allowed. But you have to go through that one. And if the electron is going to spin change, they are not allowed. Right? If it is going from D to D, it's not allowed. S to S is not allowed. Okay. So those things are summarized in that form. They are called spin rule. Delta should be same. That means not going to change. If there is an electron is going from one to another one, if there's a vacant one without an electron, it doesn't have to change the spin. You go and stay there. But if there's an electron here, it has to change. Right? So that's the spin change. And now here from one level to another level, there should be always that D to D is not. Now, example, some octyl manganese compounds are right. Manganese are off-white. There is no color change. Pale. Why is that? So if you look at the diagram here, now it's going to be D5 system, all in unpaired Mn2 plus weak octahedral T2G3 here, EG2 here, configuration where d electrons are unpaired. So magnetic moment, you can have 5 into n plus 2, 7, right? Multiply 5, 7, 35, square. So this is right. And now, if you want to excite that downstate, that electron should go and change the state. That is not allowed. And going within the D level also not allowed. Therefore, it doesn't have any color. Very pale color. So it breaks both rules. And if you go further down, session 7, so there actually, when you are making these complex, you have metal center, you have to add ligands. If we are going to add same ligand, right, like water or ammonia or something, there are ways of joining. Can have metal center and one ligand comes and make that, and that react with another ligand, two. Likewise, you can go one by one addition, right? And you can write equilibrium constants for all of them. K1 called equilibrium constant here, and we got thermodynamic kinetic side. So just go through that, and you'll get these equations. Now we talk about M adding one, ML1, and that adding another one, like on. But we can think about another way. You have M, there are 6L all going in. So then M plus 6L Mx. So that's the other equation. So we call overall stability. So go through, that's not difficult now. We are writing equilibrium constant, concentration of that, and the concentration of that divided by that. So these are the values. When you write these equation, K2, concentration of this top, and the concentration of added L, and that. So we can go, right? Then the basic idea here, the other one that I mentioned here, overall value, beta value. We call it equilibrium and stepwise formation constant, but we get overall one. We can think about always adding number of putting 1, 2, 3 or n number. You have this equilibrium ml and concentration of that and of that. In fact, there are other ligands here. We have not included there for clarity, right? So these information will help you to get some idea about the stability of the relationship between equilibrium constant beta or overall formation constant here, the overall reaction. If you look at the rates here, the Bi equal to Ki, the relationship, we can see this particular relationship. Bn is equal to K into K2, K2, K3 from a multiplication. That pi symbol means I into 1 to I into n. We have the sigma notation, K1 plus K2. This symbol says multiply all K1 into K2 into K3 like that is I is equal 1 to n. That is beta. So that's what we got earlier. K1, K2 is equal to beta. K1, K2, K3 is equal to beta 3. Right? So we can get the relationship between overall stability constant and the earlier got K1, right? So that's actually very clearly mentioned in the book. So now already 10 minutes past. I'm going to eat up your time for Dr. Kopila. So I think I'll touch upon them later next day school as well. But go through all the notes now. Get a break at least. The factors are given. Session 8 actually we talk about the reactions. Now we know the basic idea about how they form, stability of them, kinetic aspects. Now, what you got to do actually, reaction. You have a compound, how you substitute one of them with one ligand. And what are the important ideas? So there are a few reactions. There are oxidation, reduction reaction. And substitutions and association, dissociation, oxidative additions that will be helpful for the next level. We are talking about organometallic chemistry, where we have a hydrogen. It can add on to a metal center, having a coordination number increase and the oxidation number increase. So we got oxidative addition. They are not common in your organic chemistry notes, right? So these are new concepts which you will learn at level 5 when you are doing organometric. But I have given some introduction here, and the very other unique ones actually reductive elimination. You can reductively eliminate these hydrogen and you can go back. They are basically reversible processes, right? And now we have another one concept called migration, or we call insertion. This carbon monoxide can insert into that bond and make a vacant site and something new ligand coming in. When this comes in, methane migrates here and that's occupied by that. So they are another reaction. And then you can have free radical reactions and so on. And the stability of these complexes can be touched upon. And there's another one actually, trans effect. The trans effect says if you have this sort of a compound, square plane compound, we have talked about trans effect, particularly square plane complex. If you have L, now for example, this particular compound, we don't bother about the charge and everything, right? We have 3 ligands of X kind, and there's a L, and we are going to put Y here. See, where does it go, right? If the trans effect is higher from L, it will replace this, and the Y will come and stay here. The trans effect is higher in L. Now, L has a larger trans effect, and X will be removed, and Y will be occupying that. If the trans effect of X is larger than L, there are 2 possibilities. X in front of that is remove this X and get Y get. Or might be this is so weak, X can remove this L and Y getting here, then we have the X. So the trans effect means it pushed out the ligand transfer and the substitution takes place at that. Right? So I think I must stop here now. And then look at now some sort of geometry. I think just to check your knowledge, you can see now what is the coordination number of this platinum here. I need quick answers. There's a platinum center. What is the coordination number? Number of atom joints. How many? 4.
Sorry.
And it's going to be answer is 4. Although you have written is platinum Cl2En, En is a bidentate ligand. So the coordination number of that particular ligand is 2. So I have seen most of the people make that mistake and look at that formula and say 1 ligand, there are 2 and coordination number is wrong. Number of electron pairs going. And what is the oxidation number of platinum here? Oxidation number 2 plus. So oxidation number is 2 plus, right? And the geometry is square plane. So when you look at the compound, always think about the basic ones. You can calculate the En number or the valence electron count and so on. So now here the geometry. Now this is the salt. Now we have two CLs. I talk about substitution. you can get another EN ligand and push them out. And then you have a substitution. And they are occupying outside that. So this will become solved, incoming ligand, EN ligand, and replace these two and coordinate it here. And then you have Cl outside. So how to write the equation, platinum, En2, within brackets, we have the Cl12. The coordination number of platinum here, 4 again. Oxidation number will be 2. Likewise, look at the cover page and you better write the oxidation numbers, coordination numbers, and the nomenclature. If you try out yourself, then you should be able to looking at the cover page, and you are given now delta T versus delta. There's a picture here, and the optical isomers are given here. FACMA is given here, and the valence point calculation also given. So, looking at the cover page, you should be able to see where these sessions are and what are the information given in these sessions. That pi star 1 is for hunting, right? And the valence bond theory is there at the bottom for nickel cyanide 4 to 2 minus, right? And how is the hybridization? It's going to be DSP2. If you work it out nicely, it's going to be DSP2, square plane, and so on. And you should know how to calculate the group number and the number of d electrons in a system now, right? So I think I have touched upon most of the things. Within 2 hours, it's difficult to go through the whole book. And it's going to, for you to go through and come prepared for the, what do you call the question and answer session. You try out your, so I can probably stop here now, then they can record. And you can meet another 10 minutes time, right? Okay. So you have given us 10 minutes. Right? Huh? We can have a break, or without a break, you can join. Yeah. Okay. I'll leave it. Okay, right. Okay, good luck to all of you. I must go. Dr. Kokla Ranasinghe will continue now. Please stay tuned now.
Let's take a 5-minute break. You can have a cup of water or tea and come back, go to the washroom and come back. 5 minutes, okay? We will start at 3:25. 3:25. पेन के eject करेगा So 50% from the CAT and also 20% of the final exam will be coming from unit 3. So that's sort of a motivation for you to study well. All right. Okay. All right. So this unit 3 is about crystalline solid. So basically, but the title is structure of solids. So when we say solids, two major categories are there: crystalline and amorphous. Crystalline means that they are the atoms or molecules or ions within that matter, the substance, they are in a long range order, meaning they are in a pattern. Okay. Opposite to that, amorphous means there is no long range pattern like glass. Okay. Right. So though the topic is structure of solids, we will mainly focus on crystalline solids because there are a lot to learn about crystalline solids. How we describe a crystal, what are the properties and all. Okay. So when you describe crystals or crystalline solid, the starting unit or the smallest building block is called unit cells. There are certain characteristics for a unit cell. Okay. So I have listed all 5 of them. All right. So assuming that you have already read the book, you should have some kind of idea what is a unit cell. So that is an imaginary block, imaginary unit. So you draw the unit cell within a crystal structure. Okay. There are no unit cell actually existing. Okay. There are only ions or atoms or molecules in a crystal solid. We draw unit cells for our convenience so that we can explain a crystal to somebody else. Okay. So when you draw a unit cell, these are the important features. It should be able to completely fill the space. There shouldn't be any gaps. If you take a piece of matter, and if you draw unit cells, that one single unit cell should be able to, like, by repeating it, you should be able to complete the material without any gaps. One. And then secondly, all the unit cells that I'm talking about should be identical. Like if you select one unit cell and it is going to cover the whole matter, all those unit cells, individual ones, they should be identical geometrically. Okay. And third, they only change by translation. That means by pushing and pulling only, you should be able to go to the next unit cell. Okay, let's say this is the unit cell we are talking about. Let me see whether I can write on here. Okay, so if this is the unit cell you are talking about, by pushing it this way, you go to you can superimpose it into the next unit cell. Pushing and pulling, that's what translation means. Okay, so you cannot rotate or anything. By pushing and pulling, you should each unit cell can be superimposed. Okay, and then the fourth one about symmetry. Well, you haven't learned about symmetry yet, so maybe you don't understand that the last unit of this course is symmetry. After learning symmetry only, you might get an idea. So I will not talk about that, but it's not necessary to understand today's content. Last one, chemical composition. So chemical composition means, like, what are the elements present in that metal or material, and what is the stoichiometry. So that overall matter composition should be same, should be present within the unit cell also. As an example, let's say sodium chloride. So what is the chemical composition of sodium chloride? Sodium chloride? What is the composition of sodium chloride, students? What is the composition of sodium chloride? Students, can you hear me?
Sodium plus, chlorine minus.
One sodium atom, one chloride atom. So if that is the material's composition, within the unit cell also, you should at least have one sodium atom, one chloride. The composition should be the same. Okay. There can be several formula units within a unit cell. It is possible that you have 3 sodium chloride units within a unit cell. But what I mean is that chemical composition, 1-to-1 ratio of sodium and chloride, it should maintain within the unit cell also. Okay. Now here are some pictures of a 2D crystal form of sodium chloride. By 2D, only the length and the width is given. The height is not there. So written on the plane sheet. So this is 2D. Now let's say that purple color atoms, dots indicate sodium and white color dots indicate chloride. So based on those 5 criteria I told you, 5 characteristics, you can draw several unit cells for sodium chloride. See this B, C, D, E, all these are accurate unit cells that you can draw for sodium chloride. All these unit cells, 4 types, fulfill those 5 characteristics. Now let's take D within a unit cell. Now look at these. The adjacent unit cells are geometrically identical. Okay, that ticks off. And also by pushing one unit cell to the other, pushing and pulling only, you can superimpose these unit cells. Right? You don't have to rotate or anything. All the atomic positions are the same. And look at the composition. 2 sodium atoms, 2 chloride atoms. So 1-to-1 ratio is maintained. What else? Geometrically similar. Do they fill the space without gaps? Yes, their boundaries are the same. They are aligned. So no gaps. So do you agree all these? If you carefully go through, we don't have time to go one by one, but if you carefully go through, all these match that condition. Now look at E. So this one, it looks different, but I tell you, this unit cell is also okay for sodium chloride. Look at this one. So at the center of the unit cell, you have 1 chloride atom. What about sodium? The chemical composition should be 1-to-1. So there is only 1 chloride. What about sodium? There are 4 sodium atoms at the corner of the unit cell. So how many sodium atoms are there per unit cell? Is it 4? What do you all think? Now you have to talk, okay? This is a discussion. What do you all think? Well, the thing is, each sodium atom is at a corner and it is shared by 4 neighboring unit cells. So each sodium atom is worth 1/4 and contributing 1/4 for each unit cell. You all agree? So 1/4 into 1/4 contribution, and there are 4 such atoms per unit cell. So the overall there is 1 sodium atom per unit cell. So 1-to-1 requirement is fulfilled. Now later you can leisurely carefully look through B through E and see whether they fulfill all the conditions. Now this F1, this F picture shows some inaccurate unit cells. Can you all guess why they are not good? Look at the first row. This one. What is wrong with these unit cells? Quickly, I want answers. Without answers, I can't go forward. What is wrong with this unit cell? Students? Answer quickly.
The ratio
There are
is
gaps.
2 to 2.
There are gaps, so not good. What about this row? Look at this first unit cell and second one, where the gap problem is not there. What is the problem there? One and 2 unit cells, are they identical? Geometrically, they are okay, but are they identical? Can you get the second one through translation? Meaning, if you push unit 1 towards the unit 2, will they superimpose? No, right? Because look at the top right corner, it's a chloride. But in the second unit cell, at the top right corner, what do you have? Huh? What do you have? In the first unit cell, top right corner, you have a chloride. In the second unit cell, in the top right corner, you have a
Sodium.
sodium. So, yeah, they are not identical. You can't get them through translation. So that's not a good unit cell. Likewise, you have to understand how a unit cell works. So there can be several unit cells for a material, but all they have to have those 5 conditions fulfilled. Okay. Now this is a 2D crystal form. But in reality, sodium chloride is a 3D crystal, and this is the actual unit cell of sodium chloride. You can see that there are, like in places, sodium and chloride are there. We will learn a little bit more about this later. So this unit cell, we call it a cubic unit cell. Why cubic? All the length, width, and height are the same. AAA. And angles are also, we call them unit cell parameters. These 3 lengths and angles related to that. They are called what you call unit cell parameters. They are 90 degrees. This angle, and this angle. They are all 90 degrees. So we call it unit cell, cubic unit cell. Similarly, there are 7 unit cell types based on, wait, I'm having trouble here. Is this? Okay, similarly, based on the unit cell shape, there are 7 types. We call them 7 crystal systems. I will not go into details one by one, but you can see that the unit cell parameters are different. Okay, so lengths and angles are different. So based on that, there are 7 types. Now, in addition to this, now within these unit cells, in an actual material, unit cells are not empty. They contain chemical substances. What are, like, chemical species? Atoms. Those could be atoms. Those could be molecules or ions. Right? So we will see how these are arranged within unit cells. Now, before that, I want to introduce you to a new concept: lattice points. Lattice points and lattices. Now, what are lattice points? So these lattice points are imaginary points. So when you draw unit cells by joining lattice points, okay? Lattice points are imaginary points. You draw unit cells by joining lattice points. Now then we have to see what are these imaginary lattice points. Now I told you unit cells are not empty. They contain ions or atoms or molecules, right? So the lattice points are drawn to represent these chemical species. We call them motifs, chemical motifs. Why the term motif? Because it represents everything: atoms, ions, molecules. So in the material, in the substance, to represent certain atoms, ions, or molecules, we draw lattice points. Okay, these lattice points, the neighborhood surrounding of lattice points are equivalent, similar, identical. Okay. Now, as an example, look at this molecular structure. See, it's a solid containing molecules. So molecules are arranged in a nice pattern. So representing this one molecule, if we draw one lattice point, and for each of the molecule, now it is represented by one single point. So that is an imaginary point drawn there to represent the whole molecule. Okay, so then you get an array of lattice points, this blue color array. So we call those lattices, like, when you draw them, like, join them, we call it lattices. Okay, then lattice planes. The term lattice plane is also come into play. Lattice plane means a plane that is being drawn based on the lattice points. Okay. Now, the thing is, these lattice points are the ones that create unit cells. You join lattice points to make unit cells. Remember, I told you unit cells are also imaginary. Lattice points are also imaginary. Then what is real? Real things are chemical motifs, atoms, ions, or molecules. The key thing that you need to know here, because many students get this wrong, atoms are not lattice point always. It is possible that in certain cases, you draw lattice points on the places where the atoms are. In that case, atoms are equivalent to lattice. But that is not always the case. There could be certain cases that one lattice point indicate a whole molecule or a pair of ions. Okay, I hope you will understand later by looking at many examples. Now here is a sodium chloride material. Alternatively, sodium chloride are there. You can draw a lattice point on the place where the chlorides. Then it's a set of lattice points, an array. Then you can draw lattice points where the sodium atoms are. Then it's a different array of lattice points. Or you can draw a point here in the middle representing both chloride and sodium. Then you will get another array of lattice points. The only requirement is when you draw lattice points, they should have identical surroundings. That's the only requirement. Okay, I hope you understand. Then what is the other thing that you should know? Lattice points are the connection points between unit cells. So when you have a unit cell like this for a matter, for a substance, it doesn't mean that these black dots are atoms. It could be in certain cases, but it is not correct always. Okay? All right, I hope that this clears up some of the misconceptions you have. Right, moving on. Now we understand what a unit cell is. We understand what lattice points are. Let me tell you something else. Now we have 7 crystal systems based on the shape of a unit cell, right? Then there is another classification. Now, I told you that unit cells are not empty. It contains chemical motifs. Those would be atoms, ions, or molecules. And also, unit cells are drawn based on lattice points, right? You join lattice points, certain lattice points to get unit cells. Based on how lattice points are arranged within a unit cell, there are 4 major unit cell types. We call them centering, okay? So this is based on how lattice points are arranged within unit cells. So the first one is primitive unit cell. In the primitive unit cell, the lattice points are only at the corners, 8 corners. Now, this lattice point could be atom, or it could be representing an ion pair, or it could be representing a molecule. Okay, don't confuse that. This is not always atoms. Lattice points. So there are lattice points in the each corner, 8 corner of the unit cell. If that is the case, we call it a primitive unit cell. In a body centered, in addition to those corner lattice points, there is a lattice point, another lattice point at the center. Okay. All right. Likewise, you have all side face centered, which we represent using F, or also single side face centered. All right. There are 4 centering types. So there are 7 crystal systems based on the shape. Then there are 4 different categories based on the arrangement of the lattice points. So these combinations give you various lattices. There are many combinations, but in reality, based on the existence of materials, there are only 14 various lattices available in the world, in the whole universe. Now, this nice diagram I got from the internet explains everything. See, each row is based on a crystal system. Each column here is based on the centering. Primitive, base-centered means single-sided. body centered and face centered, meaning all face centered. So only certain Bravier's lattices are available in reality. Okay, now carefully you can later study this table. Now let's take an example. Here I got example I got is the cubic lattices. Cubic means all the in a unit cell, the length, height, width all are the same, and also all the angles are alpha, beta, gamma angles are 90. So based on centering, these are some actual examples. Examples for cubic primitive lattice is cesium chloride. Look at the structure, cesium chloride. So all the corners have a chloride atom. All right. Why do we call this primitive? Because there is another atom in the center. Why don't we call this body center? Why it is primitive? Can someone tell? So cesium chloride is an example for primitive cubic lattice. Primitive cubic means the lattice points are only at the corner, 8 corners of the unit cell. So is it wrong here to use cesium chloride as an example? What do you all think? I want an answer. Why don't we consider the cesium atom as one of the lattice points? Somebody should answer. So we are
It
taking
should
out
be
of
from the same kind. The lattice points should be the same.
That's
Either
right, exactly. Yes. So the one rule about lattice points is their surroundings should be the same. They should be identical, right? So here, coincidentally, the lattice points are equivalent to chloride atom. See, this is the lattice point. It's a chloride atom, right? But this is cesium atom. They are not identical. So you cannot consider this center cesium atom as a lattice point. Okay? So only lattice point, identical lattice points are at the corners of the unit cell. Similarly, now look at this tungsten metal. Now this is a body-centered cubic lattice. Why? At the body also the same identical thing. Now look at the all face-centered F centering. The example is zinc sulfide. Now here, what is the lattice point that we are considering here? Lattice point we are considering here, it is coincide with the sulfide ion. So sulfide ions are at all the 8 corners and also on the same face center, like all the face center. But in between you have zinc atoms, but we don't consider them as lattice points because our lattice point, our definition is a sulfide atom. All right, okay. Now, what about single site center? In the world, in reality, there are no materials that has cubic single site centered lattice. So there are no actual examples. Okay. All right. Moving on. Now, calculating the number of lattice points belong to a unit cell. How do you calculate that? By the way, do you all see the topic of these slides? The online people, the topics are cleared, right? I'm asking because there is a ribbon on this screen and the on-site people can't see the topic. You all can see, right? There are no disturbances.
Yes.
Okay. Good, good. All right. Now, how to calculate the number of lattice points within a unit cell? There is a way. Now, inside the body, in the body center, if you have a lattice point, that lattice point entirely belongs to the, like in this case, as this tungsten, it entirely belongs to the unit cell. So you count it as 1. If the unit cell is on a face, that means it is going to be shared by 2 unit cells. Look at this one. This is on face, this unit cell. If you consider the whole material, it is shared by the neighboring unit cell. So only half of that unit cell will, the lattice point will be contributed to 1 unit cell. In a corner lattice point, now this is shared by 8 neighboring unit cells. So only 1/8 of the lattice point will belongs to one unit cell. Is it clear? So if your unit cell, if your lattice point is at an edge means at an edge, meaning it is going to be shared by 4 unit cells. This is an edge. If you have a unit cell here, this will be shared by all these 4 unit cells. So 1/4 contribution. So that will be important because later on when you are to calculate the formula units within a unit cell, this calculation will be important. Okay. So based on that, we will look into each of the centering types and see how many lattice points are there. Now it is primitive. If the unit cell is primitive, there are only 8 unit cells at each corner, each contributing 1/8. Therefore, 1/8 into 8 corners. For a primitive unit cell, there are only 1 lattice point belong to that unit cell. Is it clear? Is this clear? Students, is it clear?
Yes, madam.
If it is clear, then tell me about body-centered unit cell. Now, here is an example. Sorry, here is an example, body-centered. How many lattice points belong to one unit cell when it comes to body-centered?
2.
2. Why? There are corner ones, 1/8 into 8, 1, and then at the center, the entire the lattice point will belong to a unit cell. So 2. Then face centered, it's not drawn here, but it's understandable because 8 atoms in 8 corners contributing 1 plus in the face center, here in this picture, on a face, on one face, there are 2 lattice points. So each contributing half. So half into 2, 1. Here 1, 1 plus 1, 2. Okay. What about all face center? This one. How many lattice points belongs to that?
4.
4, because each face has 1 lattice point. There are 6 faces. So 6 into half, 3. 3 plus that corner 1, 4. Very good, very good. Moving on. Here is an example, like, a question. On the top, you have iron metal. Now tell me, how many iron metals belong to this unit cell? So remember, as the way you counted lattice points, you can count the chemical species also which belongs to unit cell. So similarly, how many iron atoms belong to this unit cell? How many iron atoms belongs to this unit cell? This is pure iron element. How many?
2. 2.
4. Someone is saying 4. Any other answers?
2. 2.
2. It's 2.
No.
See,
2.
there are 4 iron atoms which are going to contribute 1/8 because there are so many unit cells around. 8 of them are there. Then there are 8 such corner atoms. So 1 iron atom. And there is a body-centered one. The entire thing belongs to this unit cell. 1. So altogether, there are 2 iron atoms. So we call this is unit cell content. Okay. Now, what about this one? This is the alloy. Iron chromium alloy. This is the way the atoms are arranged within the alloy. Okay. Now, first of all, tell me this unit cell. If you are to consider that iron as the lattice point, is this a primitive unit cell, body centered, face centered, or single side face centered? This one,
Primitive.
alloy, primitive. The unit cell type is primitive. Good. Now tell me the unit cell content. How many iron atoms are there? How many chromium atoms are there per unit cell? How many iron atoms?
One
One.
each.
Then how many chromium atoms?
One.
One, because it's in the body. So what is the formula? Fe chromium. This is the chemical composition of the atom. Okay, clear? All right, moving on. I don't know whether how to keep this only for this one, but so I'm going to delete everything and may move on. All right. Here is a sodium chloride ionic solid. Look at this. This is just one unit. And here and there in certain places, sodium and chloride atoms are there. Can you calculate how many formula units are there in this unit cell? When I say formula units, our formula is sodium chloride. How many formula units are there? Meaning how many sodium chloride ion pairs are there within the unit cell? Quickly calculate. I'll give you 1 minute. So you have to calculate separately how many chlorides are there, how many sodium atoms are there. Calculate quickly. If you know the answer, let me know. How many?
Four.
Okay, tell me how many chloride atoms? 4 is correct. No, 4 is correct. 4 formula units are there. Now let's see how she came up with that answer. Let's look into the sodium atom. So in each corner we have sodium atoms. So from corner we can get 1. Okay. Plus, in addition to that, now this is correct. We have considered it. In addition, where do we see sodium atoms? On each face. Remember, see 1, 2, 3, 4, 5, 6 on the faces. So each contributes half. And there are 6 faces. That means 1 plus 3. There are 4 sodium atoms. Now what about chloride atoms? Chloride atoms, you have chloride atoms in the edge, in all the edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 chloride atoms in edges. So edge means only 1/4 contribution. Plus, there is another chloride atom at the center. Totally contribute. So 4 into 12, 3. 3 plus 1, 4. So sodium, 4 sodium. Wait. 4 sodium atoms and 4 chloride atoms. So all together there are 4 formula units. If someone asks how many formula units are there within the unit cell, this is how you calculate. Do you agree? Any questions? Any questions? Okay, moving on. Well, I have to draw these again before uploading. Anyway, let's see. All right, moving on. Okay. Density, unit cell density. The title is unit cell density, you can't see. So, is density an intensive property or extensive property? Density for a matter, is it an intensive property or extensive property?
Intensive.
Intensive. What do you mean by that? Why it is intensive?
It is not depend on the mass.
Yes. The intensive properties mean it doesn't depend on the amount of the substance. So whether you take 1 kilo, 1 gram, 1 milligram, in all those samples, the density is the same. If that is the case, since the density is an intensive property, if you take one single unit cell of the matter, still the density is the same. Okay? So what is the benefit of that? The benefit is, if you know a lot of details about the unit cell, you should be able to use those details to calculate the density of the material. Okay? So here is a nice formula. This formula can be used to calculate the unit cell density. So density is mass divided by volume. If you know the number of formula units per unit cell, meaning if you know how many molecules or ion pairs or atoms are there per unit cell, can you calculate the mass of the unit cell? If you know the number of formula units, for that you need to know the molecular mass of that material. Molar mass divided by Avogadro number. What is this? Molar mass divided by Avogadro number. What is it? It's a weight of one molecule or one formula unit. Because molecular weight means grams per mole. Weight of one mole. So if you divide the formula weight or molar mass with Avogadro number, you get mass of one formula unit. And then you multiply it by the number of formula units per unit cell. That means, what is it? The whole thing means the mass of the unit cell. Do you all agree? Do you agree? Online people, do you agree? Do you all understand this? Students, can you understand this?
Can you repeat?
Now see, formula mass or the molecular weight. Sorry, molecular weight or mole mass is mass in grams for 1 mole of the chemical substance. Okay? When you divide it by the Avogadro number, what do you get? What do you get? So
Mass of one formula.
Yeah, mass of one molecule or one ion pair or one atom, one molecular unit. Sorry, formula unit. Then if you multiply it by the number of formula units in the unit cell, what do you get? There's nothing else in this unit cell, only the material. Okay? Or if there are only 4 formula units, if you multiply it by the mass of one formula unit, you get the mass of the unit cell. Do you agree? You don't agree? What is the wrong there then? If you don't agree, let me know why. And you have to make quick, otherwise we take a lot of time to come. There are a lot of things to cover today. Do you agree or not?
Agree.
You are agreeing just to get by this. I don't know. Anyway, you think about it. Then, if you divide it by the volume of the unit cell, volume of the unit cell, you get the density of the unit cell by mass of the unit cell divided by the volume. Okay?
Yeah.
All right. So I hope you understand. So this is the way to use this. This is the way to calculate the unit cell density. If you calculate the unit cell density, that means it automatically you know the density of the material. So this concept can be used in many calculations. I want you to practice these calculations because I might ask these in the CATs or in the final exam. Look at this question. Metallic copper has FCC lattice. FCC means face-centered cubic lattice. Face-centered cubic lattice means something like this. Calculate the following if Avogadro number is 6.023 into 10 to the power 23. Atomic radius and atomic mass of copper is 128 picometer and 63.55 grams per mole, respectively. So, certain details are given. Then you are asked, they are asking you questions. Length of the unit cell. Length of the unit cell means like you have to determine the length. Like this is the unit cell. Sorry. Length of the unit cell. So this is the length of the unit cell, right? They ask you the unit of the length of the unit cell. How can you calculate that? This has nothing to do with the density. By looking at this picture, can you figure out a way to calculate the unit cell length?
The radius into 2. No.
No, that's wrong because radius is only this. There is a gap in between. You are going in the correct pathway. Think a little bit harder. Huh? Not 2, because if it is multiplied by 2, what about this gap? They are not connected one to one. Think about the diagonal. Yeah? Think about the diagonal. Not letting me draw. Someone else is drawing. Please don't behave like adults. Don't draw because I'm working here. Look at this diagonal. Okay, so this is what we want to calculate. This is something what we know because this is R, 2R, and R. Do you agree? Do you agree?
Yeah. Yeah.
What is the relationship between these two? What is the theorem? Huh?
Pythagoras.
Pythagoras theorem. Very good. Pythagoras theorem. Let me go to the next slide because I have nicely written the Pythagoras theorem applied to save some time. Okay, give me a second. Okay, this is not good. Okay, here. See, Pythagoras theorem is applied. 4r squared equals 2a squared. Do you want any help with that? Do you understand why I have written it like that? Because this is 4r. This is a. Since this is a cubic unit cell, this edge is also a. And then I have incorporated Pythagoras theorem. By solving this, you can get the value a. All right. So now we know the length of the unit cell. Then they ask you to calculate the volume of the unit cell. What is the volume of the unit cell? Huh? What is the a cube? By the way, are there no boys in this online platform? Because I only hear girls. What happened to your boys? Huh? Where are all the boys in this post? Now I want to hear from one of the boys next time. Okay, all right. So volume of the unit cell is a cube, right? Number of atoms in a unit cell. That means number of formula units. In a face-centered cubic lattice, how many formula units are there in a unit cell? In this case, how many atoms are there in this unit cell? Because this is metallic copper. How many atoms are there in a unit cell? In a face-centered cubic lattice?
4.
Yes, very good. 4 unit cells. We learned already how to do that. If you know all these information, can you calculate the density of the substance? Can you calculate? Yes. So you just simply use this formula, or you can simply use your general chemistry knowledge to calculate it. Formula weight is given. Avogadro number is constant, and you know it. Now we figure out C is 4. Then we know the volume of the unit cell. So everything is known. What you have to do is simply take out your calculator and do the calculation. But I will not let you do the calculation right now because we are far behind time. But the data is given. Okay. Here is a new question. Now, again, the same question. Okay. The key point is that you have to know that sodium chloride also has face-centered cubic unit cell system, but here the unit cell is given. So you know there are 4 formula units. Okay, 4 formula units. You know that. So 4 formula units, and they ask you to calculate the density. To calculate the density, what else do you want to know from the equation? Anything missing? Anything missing? So we know the formula weight. It's given. Avogadro number constant. Formula units, we know 4 because we calculated it previously. Volume, do we know volume? Do we know the volume?
The dimension.
The unit cell dimension is also given. Easy. This is a straightforward question, right? All the information we need are already here. So we will not waste any time here, but do the calculation at home. I'm giving the answer. You can check whether you can get this answer. If not, there is a problem in your calculation. Also, okay, moving on. Now we understand what a unit cell is and how to define a unit cell and what are the information that a unit cell will give. Now, next question is that all we understand how the atoms are arranged within a material, solid material. So we can consider atoms as spheres, right? So in a molecule also, it's a combination of atoms, right? So these atoms are in close proximity. They could be bonded, they could be electrostatically attracted, whatever the way. if these are spheres, how are they arranged? So that is when this close packing arrangement comes. It's a theory. Okay. Here are two possible arrangements. This is a square array of spheres where on top of each sphere there is another sphere. The problem with this is that the voids or empty spaces this is going to create are very huge. So they are not that efficient in packing. But in nature, the packing of these solid atoms within a solids are highly efficient, meaning they are packing in disarranged. We call it close packed layer. That is the maximum efficiency they can achieve. All right. So this is only 2D, only one layer. When it comes to actual material, these layers are coming on top of each other, layering, stacking them in 3D manner. All right. Here is actually a YouTube video. We don't have time to go through this. And also in your book, it is nicely explained. This close packing. I'm not going to spend time on that. So you can watch this video, also refer to your book and get an understanding. The bottom line is, so I'm not going to play it here. The bottom line is, based on this layering of these closed pack layers, there are two main patterns in the closed packing arrangement. One is this ABA pattern. Okay? In the layers, every other layer are coming on top of each other. ABAB layering. So we call it hexagonal close packing. The other method is cubic close packing, where the three layers are in three different orientation, like packing nature. So ABC packing. All right. So this, to understand this, you need little bit of thinking and little bit of me time. You sit down, you watch the YouTube video, you read the book again, and you understand. If I am going to spoon feed this, it will take 4 hours to do this. So you have to think yourself. Still, if you find it difficult, you can talk to me later. But today, at this point, I will not spend much time. One key thing I want to highlight is that cubic close pack arrangement, at the end of the day, it will create face-centered cubic unit cells. So if someone says FCC, that means it's cubic close pack. If someone says CCP, you can consider it as face-centered cubic packing or FCC packing for calculation purposes. All right. So when this packing is there, these close packing, the efficiency is only 74%, meaning rest of the 26 percentage is empty. It's empty. Voids are there. So these empty voids, actually you can identify as two types: octahedral voids and tetrahedral voids. These terms are there because of their shape of the void. So in both of the cubic close packing and hexagonal close packing, you are going to see these two types of voids. Okay. So octahedral voids look like octahedral because it is surrounded by 6 atoms. 6 close packed atoms are going to create octahedral voids. Tetrahedral voids are created by 4 neighboring atoms close packed together. Okay. So usually octahedral holes are bigger than tetrahedral holes. All right. Okay. So I told you that the 74% is the packing efficiency when it comes to close packing. And if you carefully look through the coordination number, it is actually loosely defined when it comes to solid structures. It is loosely defined as the number of neighboring atoms. Okay. So when it comes to hexagonal close packing, if you consider, let's say, this atom, it is on the plane, it is surrounded by 6 atoms. And at the bottom layer, there are 3 atoms. See, 3 red atoms. So on the top also, because this is AB pattern, on the top also, there are 3 atoms neighboring. So altogether 6 neighboring atoms. So the coordination number is 12. Even though you can't see it clearly from this picture, when it comes to cubic close packing also, the coordination number is 12. You can, leisurely think about it and see. All right. Then this is HCP and CCP, the most common packing types. There are other less efficient packing types also exist in nature. One of them is body-centered cubic, BCC. Its packing efficiency is only 68%. So less efficient than close packing, HCC and cubic close CCP, right? There what happens is the atoms are in a body-centered nature. You see what you can, you can clearly see. So these are representing lattice points, but these are actual spheres, how they are packed. In that case, coordination number is 8. Why do you say 8? Think about this center atom. It is surrounded by 4 upper neighbors and 4 lower neighbors. So coordination number is 8. And each and every lattice point are identical. Therefore, if you consider this one also, the coordination number is 8. You can't see it from here, but if you consider several unit cells, you will see it. Okay? All right. So many of the metals that we have, elemental metals, they have these basic structures. Hexagonal close packing, cubic close packing, or body-centered cubic close packing. Sorry, body-centered cubic packing. There are even lesser efficient packings. One is this primitive packing. Remember those square packing, meaning they are packed in a square nature. This one. This one. If you have another layer on top of this, right on top of it, you will get primitive packing. Okay? It is very less efficient. Only 52.4 packing efficiency is there. There are a lot of voids. Okay? All right. And the coordination number, if you think about it, what is the coordination number of this atom? What do you think? What is the coordination number here? Anybody? Because it's written as 6, but can you explain it? Think it like this. So when you have one atom on the same plane, you have 4 atoms like this on the plane. Then on top of you and at the below, you have 2, like 1 each. So altogether 6. Can you see that? Can you understand it? Can you understand it? See, look at this one. See, there are 4 atoms here. Similarly, there is 1 here, 1 here. And then at the bottom you have 1, and at the top also you have 1. 6. Okay? Likewise, the coordination number there is 6. All right. So we have learned about different types of packing arrangement. Then let's move on to another question. The same questions, but now some more information is there. Calculate the density of gold with a cubic close packed array of atoms of molar mass M and a cubic lattice parameter A is given. Now, what is the tricky question here? The tricky question is they didn't use the term FCC. If it is face-centered cubic only, we can use that calculation method I used. Remember, this here, 4R squared into 2A squared. You need that information, right? So you can only use this relationship if it is face-centered cubic only. Otherwise, you can't use it. Then there should be another method to calculate the relationship between the atomic radius and the unit cell length. Do you understand? This equation value, sorry, here it has to be like this. This equation value is face-centered cubic arrangement. If it is body-centered, you have to think about another way. All right. So the problem with this question is it doesn't say FCT, face center. Instead, Instead, it says cubic close packed. That is the tricky part. But as soon as cubic close packed term is there, you should know that means FCC. So then you can use the same procedure. Is that clear? Students, is that clear? Any questions?
Madam, can you explain it?
Which part you don't understand? Which part? So here, now we already know if they say the arrangement is face-centered cubic, we already learned what to do. Isn't that true? We learned already what to do if the arrangement is FCC, face-centered cubic. See, this is the calculation. We could do this because it says it is face-centered cubic. Then only this Pythagoras theorem we can apply to the relationship between R and A. Okay? But in the new question, they don't say FCC. They say cubic close packed. So we don't know what is cubic close packed, meaning, I mean, we know, but we don't know then how the atoms are arranged, like, you know, all of a sudden. That's the problem here. But I told you that if the atoms are packed in a cubic close packed array, it automatically creates FCC arrangement, face-centered cubic. That's the only tricky part here that you need to know. Once you understand that, this question is easy. All right. Clear?
Yes, madam.
Okay. Then I'm already giving you the answer. You can try this at home and see whether you get it correctly or not. Here is another question. The same question I reverted it. The density is given. The density is 19.3 grams per cubic centimeter. Calculate the atomic radius of gold, meaning they ask for the R value. They ask for the R value. If the mole mass of gold is M, now what should we do? Now we have to do the reverse. Very simple, okay? We just do the reverse. Reverse meaning, I have drawn everything, written everything. Let me go one by one. First, you have to calculate the mass of a unit. From density, you can do that, right? Not from density. Sorry, mass of the unit can be calculated because you know the atomic mass is 196.97. They have taken it as 197 divided by the Avogadro constant multiplied by the number of atoms present within the unit cell. That is 4. Why 4? Because this is cubic close pack, meaning it's FCC. Clear? Then you apply the density equation to get the volume of the unit cell. Volume of the unit cell. Once you know the volume of the unit cell, you can calculate the unit cell length. If you know the unit cell length, you can apply the equation to get the atomic radius. Clear? Any questions? I just did the same thing in reverse manner. Okay. Questions? Shall we move on? Okay. Because no time is there, I'm going to move on, but you can always disturb me and ask the questions if you have it. Now, I told you there are two types of voids in a closed pack arrangement, tetrahedral and octahedral. If you close pack n number of ions or atoms, it creates n number of octahedral holes and 2n number of tetrahedral holes. That you should know. Okay. Here I am showing you, this is a face-centered cubic close arrangement or face-centered cubic arrangement of atoms. This dark color one. Okay. When you arrange n number of ions like this, it creates 4 octahedral holes. Do you see? Because in all the edges, there is an octahedral hole. These O indicates octahedral holes. So there are 12 such edges. So 3 octahedral holes from there. And then at the center also, there is an octahedral hole. So altogether 4. If you arrange for n number of ions in a closed pack arrangement, it creates n number of octahedral holes. And it also creates 8 tetrahedral holes. Do you understand? As a rule, you just keep it in mind. Now, in reality, when ionic solids are crystallized, what happens is very interesting. What happens is that usually bigger ion, mostly it is the anion, bigger ion closely packed, creating octahedral and tetrahedral holes. Okay, so those positive ions, cations, are going to trap in these voids. That's how ionic solids are created. Bigger ion closely packed, which creating holes, and those holes are occupied by small ions, usually the cation. But it could be the other way also. It all depends on the size. Okay, that's why we calculate the radius ratio. Higher the radius ratio, you have to have, that means the cations are very big. So then you have to go for bigger holes. Okay. So based on the radius ratio, the arrangement is different. All right. So I'm not going to explain this chart. It is in your book. If you read it, you will understand. Any questions here? No, right? Here is a question for you, but before doing this question, let me show you some examples. Some ionic solids. So there are, depending on these ion arrangements, which one is getting close packed, which one are trapped in the holes, and what kind of holes are filled, occupied. Based on that, there are different ionic solid types. We are not going to discuss about all the ionic solid structures. We are only going to talk about 4 main categories. Okay. Here I have outlined 3 on this slide. First one is rock salt type. Example is sodium chloride. There are many other ionic solids that has this rock salt structure. Then zinc blend is another type. There are many other types which has this zinc blend structure. All right. Then fluoride, CaF2 nature. Okay, there are many of them. AX2 type we call. All these structures have the close packing arrangement, meaning a cubic close packing or face-centered cubic anion packing. Anions are bigger, they pack in the cubic close packing nature, FCC nature. Then those holes we have created, octahedral and tetrahedral, they are occupied by the cation. Now in the rock salt case, chloride is bigger, so they go in the FCC packing. And sodium atoms are trapped in all the octahedral holes. In the tetrahedral holes, there's nothing. They are empty. In the case of zinc sulfide, octahedral holes are empty. Half of the tetrahedral holes are occupied by the zinc atom. In the case of fluoride, octahedral holes are empty, but all the tetrahedral, 8 octahedral tetrahedral holes are occupied by the calcium. In this case, fluoride atoms. Now see, now it's reversed because the radius ratio is so high. Now the anions are not stacked. The cations are the ones that packed in the FCC manner. And within the holes, you see the fluoride atoms or anions. Okay? All right. So these are some examples. And the 4th type, I told you I will discuss four types. The other type is cesium chloride type. I hope you remember that we discussed about cesium chloride before. This is actually not close packing. This is actually primitive packing, cubic packing. Remember, this is primitive or cubic pack. less efficient packing mode because the atoms, cesium chloride atoms are so big. Okay. Then at the center, you have the cesium atom there. Okay. All right. Any questions so far? These are some common ionic solid packing types. So before going further, I have a quick question for you. This one. Try this one. What is the formula of a compound in which the element Y forms CCP lattice, meaning face-centered cubic, and atoms of X occupy 2/3 of tetrahedral voids? Now quickly do this. Now remember, if n number of atoms are close packed, it creates n number of octahedral holes and 2n number of tetrahedral holes. Now quickly do the calculation and come up with the formula. If you have the formula, just let me know. Quickly do it. Give me the answer. Do you have the answer? Answer, please. So tell me, so this is a CCP lattice. So tell me now in this Y element is closed, cubic close packed Y element. So let's say n number of Y elements, elemental atoms are there, n number. Okay? N number. Then if n amount of Y element atoms are close packed, how many octahedral atoms will holes will be created? If n number of Y atoms are cubic close packed, how many octahedral voids will it create? N. Okay, so this will create n octahedral voids. Okay, how many tetrahedral voids will it create?
2n.
2n. Out of these 2n number of tetrahedral voids, how many are occupied by the X? How many are occupied by the X atom? X atoms.
Mm.
Huh? How many? 2/3. 2/3 atoms are occupied. That means if n number of Y elements are closely packed, 2/3 of tetrahedral voids will be occupied by X, meaning there are 2n amount of tetrahedral voids. Out of that, 2/3 will be occupied by X atoms. So this number of X atoms will be there. Do you agree? Do you agree? Do you agree? So if n number of Y atoms are there in a close packed arrangement, 2n into 2/3 of X atoms will be there. Okay? Agreed?
Yes.
Okay. Then based on that, we can come up with the formula. See, I have written it already. So then you can get the ratio. All right? 4n/3 into n. So it's 4n into 3n. Meaning formula will be x4y3. Did you get it? Got it? Very good. All right, moving on. So we discussed about these. Sorry. The covalent solids. I told you when we say solid, it's not only ionic solids. Covalent solids are also there, like diamonds or graphite, where like covalent network bonds are there. All right, and also some simple molecular solids are also there. When you take sugar is a molecular solid. Okay, so there are different characteristics, chemical properties based on their bonding and all. I want you to read those. Okay. So in molecular solid, they have weak intermolecular forces. Because of that, they have low melting point, low boiling point, likewise. When it comes to covalent network solid, they are strongly bound. So they have high melting point, high boiling point, like this. Okay? All right. So here is another question about perovskite. So it explains how the calcium, oxygen, and titanium are arranged. Based on those arrangements, you can come up with the chemical formula of the mineral. We don't have time to spend on this, so I'm going to leave it. Later on at home, you just try it and get the formula and double check with my answer. Okay? Or do you want a minute to try this? Or shall we move on? Let's move on, no? The question is there, you come up with the answer. Answer is already I gave you, but I'm going to leave it for now. Now we will move on to X-ray diffraction. Now, we sort of have some kind of idea by now how the crystal structure, atoms are arranged in a crystal structure. Now the science is so advanced, the experimental methods are advanced, we can use X-ray diffraction to actually identify these crystal structures. The unit cell dimensions, unit cell content, where the atoms are located, everything can be get from the X-ray crystallography. We call it X-ray crystallography. Now the question is, why X-ray? Why do we use X-ray for this? To identify the ionic solids. Why? What is the reason? It's in the book. Do you know why X-rays are used? Because there are so many other electromagnetic radiation in the spectrum. Why only specifically X-ray is suitable for this? What is the reason, students? Do you know? Now, here is the thing. Now, these Bragg duo, father and son, they realize then that when you expose ionic solid or a crystal solid to X-ray, the solid tends to reflect certain X-rays. Okay? The crystal solid material tends to reflect certain X-rays. And they observed a relationship between these, the angle of these X-ray beams are reflected, and also between the interplanar spacing, meaning molecular planes. They observed the relationship. That means by examining the reflection patterns of the X-ray beams, they were able to understand the unit cell. Why? Because they were able to understand atomic planes of that crystal solid. Okay, so this is the beginning. So then they were thinking, why why these X-rays are reflected from the atomic planes. What is the reason? The reason is diffraction. The reason is diffraction. Now, then next question is, now I use two terms, reflection, diffraction. So reflection means now, like, you know, as you see on the mirror, the reflection, the whatever is incident coming in the same angle, they go out, reflection. Okay. So they saw certain X-rays are reflected from out of the material, crystals or solids. They couldn't understand why. Later they realized it is because this diffraction of waves. Diffraction meaning that when the waves go through a obstacle like this slit, see, this is there's a hole there. When it goes through the hole, the waves bend. If there are many more holes, the many bending will occur. Okay. So this bending of the waves when it passes through obstacle is called diffraction. Okay. Diffraction occurs when the wavelength of that radiation is in the same magnitude as the slit or the hole that it is going to. Okay. If the slit length is in the same magnitude as the wavelength of the light that it is going through, the diffraction occurs. Okay. Now, in the crystal structure, we have atoms in a pattern, right? And in between patterns, in between atoms, what do we have? Slits, voids, isn't it? Those voids are in the atomic length, what you call the bond length. All right, in the 10 to the power minus 8, 10 to the power minus 12 range, bonding range. Okay, the X-ray wavelengths are also in that same wavelength range, length range. Okay, so interatomic distances or the bonding lengths are also in the same magnitude as the X-ray wavelength. That means when X-ray is incident on a piece of ionic or solid, the atomic planes can diffract the X-ray radiation. But it cannot happen to other electromagnetic radiation waves like, you know, visible light or infrared or UV. Why? Because their wavelengths are not compatible with the interatomic distance or bonding distance. This only happens because X-ray wavelengths are in the same magnitude as the interatomic distance. Because of that, now in a pattern in the solid material, there are several atoms in the long range pattern. So it looks like it has so many slits like this. So many slits. And when the X-ray is illuminated, it is going to be there will be so many diffractions. Okay. So when a wave is diffracted, two things can, like, you know, they interfere. Like, you know, there are several bending. Sorry. So there are several, like, you know, these diffractions come like this, and there are so many waves merging with each other. Then here comes the phenomenon interference. So when these diffracted wavelengths are merging with each other like this, they interfere. There are two types of interference, constructive and destructive. If they are in the same phase, the waves will interfere constructively, having higher amplitude. I'm not going to discuss these physics with you, but what I'm saying is, when the X-rays are incident in certain angles, they diffract and create, interfere and create stronger or not stronger, highly intense wavelengths, high amplitude wavelengths due to constructive interference. And they come out, they look like as they are reflected from the material. So if you collect those constructively interfered wavelengths, that will give you an idea about the interatomic planes. Okay, that is what Bragg's equation is about. I hope now you explain why X-rays are used to study crystal structures. Now the Bragg duo, father and son, they studied this phenomenon and they came up with this equation. N lambda equals 2d sine theta. Here lambda is the X-ray wavelength. D is the interatomic distance or distance between two atomic planes. Sine theta. Theta is the glancing angle or angle at which X-rays fall on the crystal. And n is an integer value. It could be 1, 2, 3, 4. It's like, you know, it's called the order of the interference or reflection. Okay. Right. Now you should know how to use this equation. Let's look at this question. A first order reflection from the 1, 1, 1 plane. So these are called Miller indices. I didn't teach you about that Miller indices yet. We are going to do that in a minute. Just think about it as this is an atomic plane. This is the name of that plane. Just think it like that way. Planes of a cubic crystal was observed at a glancing angle of 11.2 degrees. When this X-ray, copper K alpha, that is the name of the X-ray beam, of wavelength 154 picometer were used. What is the spacing between the atomic planes? So this is very straightforward. All the data is given, you just simply have to apply. First order means n equals 1. Okay. This is the glancing angle theta. This is the lambda. They ask for D. Can you do this question? N is known, lambda is given, theta is given. Can you calculate the D? Interatomic spacing. Yes, you should be able to. Okay. All right. So that is the question there. And I don't know whether I have the answer. Let's see. Yes, answer is this. You can do it at home and see. All right. All right. Now, interplanar spacing D. So for different kind of crystal systems, the equation for interplanar spacing D is different. Okay. Here, this equation is for cubic crystal system. Cubic means that all the lengths are the same. The alpha, beta, gamma are 90 degrees. For this cubic crystal system, this is the equation for interplanar distance D. Now, you all know what A is. What is A? What is A? What is A? Guys, what is A? What is A in what is A? Now we have been using this A for a while. What is it? In the cubic unit cell, what is A?
Length.
Unit cell
Length.
Then you might have a question. What are these? H, K, L. What are these? If you read the book, you already know. What are those H, K, L? Miller indices for planes. Now within a unit cell, you will know later that we can define these Miller planes. They are also imaginary planes with identical lattice points. Okay, Miller planes. So these Miller planes have a name. Those are 3 parameters which we call Miller indices. Okay, we are going to learn about them. So in this cubic unit cell, if the Miller planes are HKL, we can calculate the interplanar distances between two planes, two adjacent planes. Okay, if we know the Miller index value for that plane, and if you know the unit cell length, you can calculate the interplanar distance, or the distance between two adjacent planes. Okay, all right. So this is the equation about. Now, why I gave you this is so because you can relate this interplanar distancing equation and the Bragg equation. How? Because both contain the D. All right. So the next question is from that. Oops. Here I modified that question. The same question I modified. What is the modification? A first order reflection from the 1, 1, 1 planes of a cubic crystal was observed at a glancing angle of 11.2 degrees when X-rays of wavelength 154 picometer were used. What is the length of the side of the unit cell? Now I am asking the D value. I am asking the, no, not D value. I am asking cell edge value, A. What you have to do is you have to combine these two. Why? From this equation you get D. And can you apply that D over here? Yes. And do you know the HKL values? You know, because the Miller index is given 1, 1, 1. So based on that, you calculate A? Yes, you can. So if I rearrange these two equations real quick, let me do it real quick. So in the first one, if I isolate D from the first equation, it will be n lambda divided by 2 sine theta. If I get D from the second equation, isolate second equation, it will be D equals A divided by H square plus K square plus L square root. Am I right? Am I right? So we can relate 1 and 2. Then you get n lambda divided by 2 sine theta equals A divided by square root of these Miller values, Miller index values. With this, you can get the A. All right. So I'm going to leave it right now here like this. You can do the question later and come up with the answer. When I upload this presentation, I will upload the answer for this one also, because I don't have it right now in the slide, but I will do it. I will give the answer so that you can try. Right, we are moving on to the next section, defects in crystals. Now you see, students, I will not spend a lot of time on this because this is basically a very simple idea, defects, by reading the book. Okay, because I want to do some work, do some Miller index calculations with you. So I'm going to quickly move on from the defects. Okay, just learn that there are no perfect crystals in reality. Always defects are there. Why? Thermodynamically, defects are encouraged because the presence of defects will lower the Gibbs free energy of the crystal. Okay, only that part I will discuss. Everything else you can, have a flow chart like this based on the information given in your book. Okay, anybody has any questions about defects? Because I don't want to spend time here, then I will not have time to work on Miller indexes. Shall I move on? This defects part is easy, right? Do you want me to go through? See, everything is in the book. Okay, I just summarized everything. If I have time, I would like to go through, but I don't have time. Is it okay if I may quickly go to the next section? Anybody wants any explanation about defects? I'm going to explain this because this is somewhat little difficult, but other than that, I will not go one by one on all the defects. Okay. All right. So I told you defects formation is favored thermodynamically, meaning in nature, because the presence of defects will lower the Gibbs free energy of material. Therefore, they like to have defects. And naturally, it happens, spontaneous. Okay? Let's see why. Now, this is the Gibbs energy equation, right? Delta G equals delta H enthalpy change minus temperature into entropy change. Now, when the defects are there, the introduction of defects to a crystal structure, pattern structure, will increase the delta H value enthalpy because it disturbs the crystal lattice. Now, delta H is the formation, lattice formation enthalpy. If you break the lattice to introduce defects, that will disturb the lattice energy, so it will increase. It's endothermic. Okay. Formation of defects is endothermic because it disturb the lattice. So formation of defects will increase the delta H. But it also increases the entropy. Entropy is a measure of randomness. I hope you remember. Higher the randomness or the higher the disorder, higher the entropy. Okay. So when you introduce defects, it increases the delta S. If this is increases, because delta is measure of randomness. Okay. When you increase the defects, delta S increases. If you increase the delta S, the total negativity will be high. So this will negatively increase. So negativity will be high. If this value is highly negative, the delta G will be negative. Higher the delta G negativity, that means more spontaneous the reaction. So defect formation is encouraged. It is spontaneous. It happens naturally. Okay? Any questions with that? Any questions? Any questions, guys? Okay, let's move on. Let's move on to the Miller indexes. Miller indices. Okay? This is a practice question. The answers are also given. You can leisurely do it at home. Okay, lattice planes and Miller indices. Now, lattice planes are like, remember I introduced you the lattice points. So when you join the lattice points, you get lattices like, lattice planes. Those are also imaginary. But within a unit cell, there are so many lattice planes you can draw. They are important because sometimes these lattice planes are coincide with atomic planes, meaning then where the atoms are, right? So this Miller indices is a way of giving a name to that lattice plane. So once I say 1, 2, 1 lattice plane, then the student knows what I'm talking about. So it's a name. Okay. All right. So here you can see these are 2D lattice planes because it's drawn on a place like on a sheet. Then when it comes to 3D, again there will be numbers. Okay. So we call them HKL numbers. We will see what are these HKL values are. Okay. When you are come up with Miller index values, what you have to do is, first of all, you have to select a unit cell, okay, and then come up with an origin. So when you select the origin should be defined, like any of these corners can be taken as origins, but what you are going to take is the one closest to the plane that you are interested. Okay, so this is the plane that we are interested. So we are going to select this closest corner to be the origin. Okay, so see what is this? The larger plane. They have the same Miller indexes. They are parallel to each other. Remember that D value I told you? That is the distance between these two planes. Inter-atomic plane value. Okay. All right. Interplanar distances mean the distance between these two. They have the same identical Miller index values. I'll tell you what. Okay. So anyway, now this is the plane that we are interested. So we chose the closest corner as the origin. All right. Then you should know, based on that, you should know how you define the X, Y, Z. Now in this case, this is 0, 0. And they have defined this as one axis, this as y-axis, this as z-axis. It's important the way you define. I'll tell you why it is important. Okay, later I will tell you. Right? So you have to define x, y, z and the origin. Then what do you do? Then you find the intersection of each of these axes by the plane. All right. Write these intersections as fractions of the cell edge. You write it as fractions of the cell edges. Now let's take the first one, the x-axis. So x-axis is cut here, halfway from the full length. So we have written it as a fraction of the cell length, a divided by 2, a half. Okay, fraction. Then let's take the y-axis. Now y-axis is cut at the edge. So that is a B, complete B, because it is cut at the one length of the edge length. Okay. Then what about the y-axis? Y-axis is cut over here. Sorry. 1/3 of the cell length. C divided by 3. Okay. Agreed? If you don't agree, let me know. All right. So now, I didn't say that this is QD. This can be used for any kind of crystal system. It doesn't have to be the QD. All right. This is for any kind of crystal system. You can use Miller indices. Okay. All right. Then those are the intersections. Okay. Intersections. Then you are going to come up with fractional intersections. Fractional intersections. What are fractional intersections? That is the ratio between the intersections and the full length of the cell edge. Okay. So fractional intersections are, now I'm going to write X, Y, Z. So intersections are A over 2, B, C over 3. Okay, then we are going to calculate fractional intersections. Those will be A over 2 divided by the cell length, B divided by B, C over 3 divided by C. Then what is the answer? Half, 1, 1/3. These are the fractional intersections. Then you get the reciprocal of these fractional intersections. Reciprocals will be upside down. 2, 1, 3. So those are
Excuse me,
your,
Bhatta.
yes.
There in the B1, there are two intersections. No? So which length we are taking there?
The B1, why do you say that there are two? This.
That means which intersection you say? The first one. That means the first part which cuts the y-axis.
So in the x direction, it's A over 2.
Yeah.
In the B1, so even though it's drawn like this, it's not cut here, okay? Just use your 3D imagination. It cuts at the corner here.
Okay.
Okay? So it's the
Yeah.
way it's drawn, but it doesn't mean that it's cut here. All right? Got it?
Yeah, okay.
It's not cut here. All right? Okay. Right. So then the reciprocal value is your next value. So the way you write is 2, 1, 3 within brackets, no commas. Okay? All right. Now shall we do a practice practice question to practice this? Well, this one I already did. So this is another example. You can look into this later. But let's do a practice question. First do this one, example 2. Come up with the Miller index for this plane that's drawn. So x, y, z is given. So automatically this will be the origin 0, 0. Okay. All right. Now do it real quick. And if you have the answer, let me know. If you have the answer, let me know for the first one, example 2. They say this is a cubic.
211.
Huh? What is it?
Is it 211?
2, 1.
No, let's see 211. Oh, it's not given here, isn't it? I thought I have written. Yes, it's 211. Yes, correct. Did you get it? Ah, very good. 211. Yes, very good. Others can also try. Okay. What about the example 3? You can try the example 3. In this case, the picture is not given. They have given us the intercepts. Then you have to get the fractional intercepts and then reciprocal. That will give you the Miller index. Quickly do that. So intercepts are A, 3/4 of B, and then half C. Oh, wait. I've done something wrong. Three-quarter of B and half C. Okay, this is the intercepts. Fractional intercepts would be dividing them in the individual unit cell length. So you get 3/4, 1/2. Yeah. So if you get the reciprocal, you get 4/3.
Ma'am, it should be divided by 3/4 B, no?
Sorry?
The 3B/4 should be divided by again 3B/4 now.
No, unit cell length. So this is the intercept. Unit cell length. That unit cell, the cell length is B, not 3/B. The full length is B. The plane is cut the edge at the 3/4. Okay. So this is the full length. A, B, C are the full unit cell lengths. Okay. When you get the fractional intercepts by dividing it with the unit cell length. Okay. That's what we did. Clear or not?
Ma'am, their Y length is 3/4 B now. So
Y length is 3D/4. 3/4. Yeah. So I don't understand the question. Is it okay? This is simple arithmetic. Maybe you have to think about it a little bit. Where's the problem? Can you tell me again?
okay, ma'am, I'll check it.
Yeah, you check it and let me know. It's just simple O-level mathematics. So once you get these values, we have a problem here. This is 4/3. Now you need to get rid of the fractions. So you multiply the whole thing by 3. So then you get 3, 4, 6. That's the Miller index. Okay. All right. Now let's move on. If there are no questions, let's move on. Draw 0, 1, 2 plane. So when this question comes, it's the other way around. So you are given the Miller index. Then what do? You do the reverse pathway. So you first take the reciprocal and then make it into the intersectional fractions, fractional sections, and then you get the intersections. All right. So the 0 means, that's a tricky one. 0 means it doesn't cut the unit cell length. Okay, because when you take, sorry, what is it? So when you take, when you take the reciprocal, it will be 1/0, 1/1, 1/2, right? 1/0 means infinity. So it never cuts the plane. That plane never cuts the cell which A. It is going to parallel. So B, it will cut at B length. Half means it will cut the C length. Let's say the cell length is C, half of the C. Okay, so these are the intersections. So here I have the plane drawn here. See, you can see like even though you can't see it nicely, this is halfway, okay? Halfway along the sea. It doesn't look like halfway, right? Because the box is not exactly cubic, but this is halfway. Oh, sorry. This is half C. See, in the x-axis, it never touches the x-axis. It never cuts. So that's why infinity is there. So in the y-axis, it cuts at exactly B position, meaning one full length. So this will be the 0, 0 position. Okay. All right. Any questions? If not, let's move on. I want to show you another thing. Where the negative Miller indices come? Bar values. So look at this question. So you have this plane, you want to write the Miller indices, but the problem is the origin that they have selected is this one far away from the plane. This is not correct. You have to pick the closest one. So the closest origin would be this one. So they are going to have a new origin here. All right. But if this is the origin, all right, if this is the origin, X, Y, C are these, the directions are now going the other way. So the Y will be in this direction, but your plane is in the back, like your plane will meet if you go backward. So that's when the negative Miller indices come. Okay. Here in the case X also like that. Your x-axis is going this direction, but you can meet the plane when you go backward. So then it becomes negative values. Okay, intersections will be negative. So here I got this directly from the book. Okay, directly from the book. In that case, since you are going backward, in the case of X, you go one cell length backward. So it will be -1. In the case of y-axis, along the y-axis, you go halfway backward. So you get -½ In the case of Z, no problem. You go in the correct direction, one length, 1 unit length. So it will be 1. So when you get the reciprocals, you get -1, -2, 1. But usually rather than writing minus, we use the term bar. Bar 1, bar 2, 1. So this is how the Miller indices are written for this plane. Okay. So this is what I wanted to tell you. I'm glad that we could end the session like, right on time. Any more questions? Wait. What happened? Did I exit? I know. I want to talk about the cat paper. So sir told you many things. One thing I want to highlight is that there is a model paper on the Learn OUS website. Model paper is already given. Okay, I uploaded yesterday only, so you might didn't see it, but it's there. Model paper is there. Paper uploaded. Model in the sense you just get the nature of the questions from that. There will be 15 MCQs, 8 from Unit 1, 7 from Unit 3, then 2 structured questions, 1 from Unit 3, 1 from Unit 1. So look into that model paper and see the structure. This is there. I'm not telling that those questions in the model paper will come on Cat 1. Okay, that's not what I'm saying. It's there for you to get an idea. It doesn't matter to you because you are not going to write it. Okay, any more questions? If not, we can finish this session. Any more questions? So shall we wrap up? Students? Any questions? No questions? So then we will stop the meeting. Okay?
Thank you.
Okay, sure. Okay, all right.
Thank you so much, madam.
Okay.
Thank you, madam.
All right. I'm going to end this.